becomes energy. Okay, Engineer, you just started recording, right?
Continue, please.
Okay. Okay, so let me just explain this exercise. It's asking us what is the cost of 5 kilowatt load at continuous operation in 1 year, in a year. Okay, 5 kilowatts, that's power. So we first of all want to calculate what the energy is. So we have to determine the total number of hours in a year, and that's what we just did here. 365 days times 24 hours. That will give us 8,760 hours per year. Okay. So we are also given, okay, so this is the hours per year. So we have to now convert the kilowatt that we were given, which is power, we have to convert it to energy. So we'll do 5 kilowatts times the total hours you have in a year, which is 7,860. Then we will now have 43,800 kilowatt hours. So this is energy. Why 5 kilowatts is power? Okay. So now this is the total consumption of that facility in 1 year. Okay. So now we have to determine the cost of consuming this amount of energy in a year. And we are told that a unit of this energy is 0.1 USD, okay, or 10 cents, 10 USD cents. Okay, so we multiply this quantity of energy by the amount per unit, which is sorry, this should be point, not comma. This is 0.1 USD. Okay, so we will do that multiplication. We're going to get $4,360. Okay, so this is just a simple calculation. On our own, we can try our hands on it. So now let's get into the main business of PV, which is solar PV application and design. I did this brief introduction about energy and power, just so that we can recap on some of these terminologies, because as we go along the training, along the program, we'll begin to use some of this energy and power and all of that. So here is a brief introduction to the course. Photovoltaic or PV, as most of us know, is a technology which generates electricity directly from the sun via the photoelectric effect. Okay. Now, come to think of this, if we can transform electricity into light through your light bulbs, okay, then it could also be possible to transform the light back to electricity. Okay, and that's where the concept of solar system now came to place. Okay. So we have a process of doing that, which is now the photoelectric effect. So the photovoltaic module, which is made up of photovoltaic cells, transforms solar energy into DC electricity. Now, the first step in generating electric power is, first of all, to convert the sunlight into electricity, but not the normal electricity that we use in our homes. It is a DC, direct current electricity. Okay. So another solar energy technology is solar thermal. We have to understand there are two forms of solar energy. The solar thermal is converting the sun energy into heat, not electricity. Okay. So solar thermal uses solar energy to generate heat rather than electricity. That's the difference. So you can see the picture here. It's two different forms of solar energy. One is solar voltaic, and the other is solar thermal to generate hot water. So it is important to make this clear distinction between these two very distinct, different technologies, which are often confused since they use the same source of energy, that is the solar radiation. So the electricity generated using PV can be fed into the electricity grid. So once you generate the electricity, you can actually do anything you want to do. It's conventional, anything that electricity does. So electricity from solar system can do that as well, as long as you have enough capacity in terms of inverter and maybe battery to support that facility. You can do anything from micro scale to industrial scale. It is very, very possible. So you can store these solar systems in batteries for later use in the case of nighttime use when the sun is no longer shining and all of that, or you can use them directly, while the sun is out. Then, as of 2018, the total global installed PV capacity was approximately 390 gigawatts. That's 390,000 megawatts. Please, if anyone has any question, feel free to stop me, ask your question. If you have contributions to make, feel free, okay? Let's make it interactive.
Okay, sorry. This solar thermal, this is Christopher here. The solar thermal, just like we know of the PV solar panels.
Okay.
Are we saying we have the solar panels that are also solar thermal panels, or how does this one come up? How is it found in the market generally?
Okay, so we have solar collectors. Okay, they are specifically for converting some energy into heat energy. Okay, it's different from solar PV. Solar PV is solar photovoltaic. Okay, they're separate from that. We have the solar heat collector, which we use to collect. Now, normally some of them have water flowing into the pipes, okay, and it's being heated by the sun. So the water that is flowing through the pipes harness this heat from the sun, okay, and it now discharges this heat into a collector and all of that. Okay, there are different technologies. So some of them uses different form of fluid, okay, that easily collect heat from the sun. So there are different technologies in that regard as well, but they are separate from the solar PV that we know. So I don't know if that's clear to you, Christopher.
Yes, the technology is clear, but I'm just like, I'm only wanting to know out there, you know, of everybody knows of the solar panel, that is the solar PV. So how does this solar thermal comes at? Is it in form of panels, or how is it? That's the point. That's the part that I was trying to get.
It has a different shapes and configuration from the solar panels that you know. So it's like tubes. If you look at some roof, you're going to see something like tube, you know, laid in parallel, you know, that collects this heat from the sun and then transfer the heat to a liquid, maybe water or any other liquid that you want the heat and all of that. So it's different.
Okay, thanks.
I think there is a picture here. So this way you're going to see these two technologies. Now the upper picture you're seeing are the solar panels. Then below it, this is the solar thermal collector. This is solar water heater. The one below it. Okay. So now this is for residential building. They have both solar thermal and the solar PVs mounted on their roof. So let us look at the applications of solar system. So you have an off-grid PV application. I have the on-grid connected PV systems. Now these are two different ways of implementing solar systems. Okay. So the off-grid systems mean that they don't interface with the grid. They don't have any connection with the grid. So you generate it via your solar cells. You could, okay, of course, when you generate this solar energy, it passes through what we call solar charge controller. If you're having a battery that you want to charge with this sun energy, it has to pass through a charge controller to control the amount of energy that goes to that battery so that the battery does not go bad or doesn't spoil the battery. That's just the function of the charge controller. Okay. So from the charge controller, it goes to the battery, and from the battery, it goes to an inverter. Remember, I told you that solar PVs produce electricity they produce DC electricity, direct current electricity. So for you to convert it to alternating current, you need an inverter to do that job. And that's why you need an inverter. We'll go into all of the details. This is just an overview, okay? So at the same time, you have grid connected PV system. Grid connected PV system means that it has interaction with the grid, okay? So you can generate electricity through the solar system for your home use, and sometimes you may have excess of this energy, okay? So when you have excess of this energy, you can export it to the grid. It's not applicable in Nigeria yet, but it's very, very common in US, Europe, and even South Africa and some developed countries, but it is not happening in Nigeria yet. We hope that soon we'll get to that level, but for now, no. So that's what we mean by grid connected PV system. So essentially, what grid connected system is that you can stay in your house, you generate your solar system, you take the amount that you need to power your equipment in your house, and you send the excess to the grid, I can pick that excess in my house. Maybe my house is in Abuja and you're in Lagos. Okay, now depending on the level of grid connection, okay, but let me bring it closer. If we are both in Abuja and you're at a particular location, I can receive that excess generation from you at my own location, which is different from where you are, through the grid. Okay, that's the essence of the grid. Okay, in terms of sharing that your solar energy. Now the beauty of it is that when you sell that excess capacity to the grid, you get paid for it. So it generates revenue for you. So there are different ways to connect to the grid anyway. So I'm assuming that this level now you're just connecting it from your home. So if you're connecting from your home, whatever I say to the grid, you get paid for it. Okay. So this is just to cascade it down a little bit for the off-grid connection and the grid connected PV system. So for what we have here, when you're talking about an off-grid PV systems, we're talking about most of these rural electrification projects. They are off-grid, okay, because they are not connected to the national grid. So most of them are off-grid. So you have the PV system for rural electrification. You have the systems with batteries, like your solar home systems. Those are off-grid. The MTN yellow box, these are off-grid systems, okay. There are some also systems without batteries, which are the solar water pumps. Sometimes you generate this solar electric energy and you don't use it to power your appliances. You use them to power solar pumps, okay, to pump water. That's water pumping. So in most cases, you don't need batteries for this kind of systems, okay? So all of these are classified as an off-grid application of the solar PV systems. Then you also have a standalone mini grid. So when I mean standalone mini grid, you could the same way for rural electrification, okay? But it's purely solar PV. You're dealing with purely solar PV, sometimes with storage, okay? Sometimes maybe without storage, but of course, if you don't have storage, you know that you won't be able to use that power when the sun is not shining, okay? So it all depends on the kind of categorization you want to do. But all of these are off-grid, they are not connected to the grid. Then you have the hybrid system. The hybrid system is whereby you have the solar system, you could combine it with your diesel generator. Okay, you can decide to do without storage so that when the sun is not there, the diesel generator will just come in and then fire up. Okay, so if you do the cost competitiveness of having diesel and having storage, then you can now decide which one is more competitive for you to do and all of that. Then you can also have the large PV diesel hybrid system for mini grid and industries. Okay, this one can happen in cities, not just rural communities or villages. You can also have it in cities, but in this case, it is assumed that that building or the industry is not connected to the national grid. Okay, so it's isolated. If it's connected to the national grid and that your design is also connected to the grid, then it's no longer off-grid. It now becomes a grid-connected solar system. Okay, so that is just the difference. So on the grid-connected solar system, we have distributed PV system, just like the example I gave you the other time, where you generate in your own house, you sell the excess to the grid and it becomes available to me in my own house. That is grid-connected PV system. Okay, you have the residential rooftop. Now this is under grid-connected PV system. Okay, you have the residential rooftop. You have the commercial and industrial PV systems as well. Then beyond that, you also have what called the central PV system, feeding electricity into the medium voltage grid. Now, this is where you have the large-scale PV power plants. Just the same way you have your gas power plants. You have your large-scale PV power plant, and they are feeding it directly into the grid. Okay, now all of these are grid-connected categories.
Hello, Chima.
Yeah.
Please let me just say one thing here also, just to add to what you said, because I wrote one exam last week. I think this is part of what came on the exam. I wrote one exam with Renak in Berlin. Now, for those of us who are in this class, like Chima said, there are two broad branches for PV. Those that are grid connected and the ones that are off grid. Most often people call the off grid standalone. But then if you look at the off grid, the off-grid can actually come in 3 ways. Okay, either for rural electrification, maybe a community, maybe your community in the village, you have money, you want to build a solar system that will connect within your vicinity. It's still an off-grid system. Then it can also be a standalone, which people have in their houses, the one the federal government is trying to implement. Then finally, you now have the one that's large, the one you have in Germany, in Europe, where you have, or the one they are trying to build in Zamfara also, and in Nasarawa, where you have a large expanse of land, the one they call solar farm, okay, which has nothing to do with national grid. Once it has something to do with national grid, it becomes grid connected. So it's good that we know these things very well, because it's part of the knowledge that you as a solar PV consultant, as a designer, what are you designing for? You need to know. So this characterization must be something we should get conversant with. Even within the standalone mini grid, there's also a two subdivision, which is the one that is purely PV, purely solar, and then there's a one you combine with your house generator or hybrid, which Chima will still talk about that one towards the end of the class. So I just hope that this is clear enough, and the emphasis is very is important. Okay, thank you. Go on, Chima.
Okay, thank you, Chinauche, for that. If any participants have a question or contribution, please feel free to go ahead. So still talking about this different categorization. So we have the grid connected configuration. Okay. So what are the configurations for a grid connected solar PV system? So now the grid connected PV system can have various sizes and will be located at different points in a central electricity grid. Okay. Now distributed systems are typically constructed on residential, commercial, or industrial buildings. Systems on residential buildings are usually small rooftop systems generating electricity for private consumption or for sale to the electricity utility. So I have already explained that. So this is just the write-up to back up what I've earlier said. So systems on commercial or industrial roofs are also used to either offset on-site electricity consumption or to sell electricity to the utility. However, commercial/industrial systems are often much larger than residential systems. Distributed systems are usually connected to the low voltage distribution grid. For some of us here who are already very familiar with the power systems in Nigeria, of course, you will know that we have the 330 kV line network. From there, we have the 132 kV transmission network. They will now come down to 33 kV distribution network. Okay, so if you're doing at a commercial level, in most cases, you're feeding into the 33 kV distribution network, okay, for further distribution to the, wherever it is needed, where it will now be stepped down further to 11 kV, and then the 415 and all of that. 400, not 415, and all of that. So that's just for some of us who are already in the power industry and understand the hierarchy of distribution voltages and all of that. I just decided to make this elaboration based on the fact that the statement that we have here that the distributed systems are usually connected to a low voltage distribution grid. Okay. So in all grid connected systems, the PV array is sometimes referred to as the solar generator. Like I said, when you're doing a grid connected, in most cases, it is assumed that it's just the same thing as your gas power plant, only that in this case, the primary source of energy is different. It's solar instead of gas. So in all grid connected systems, the PV array sometimes refers to as the solar generator. For see the figure, typical residential PV system. They generate DC electricity and it is connected via junction box to an inverter, which converts the direct current into alternating current. Now, the inverter output is connected to a meter, which records the amount of energy being fed into the grid. Now, in most cases, we call this net metering. I want you to take note of this word. Net metering is a very important concept when you're talking about grid-connected electricity. Now, what does net metering mean? Maybe I will update this slide and then also just add about that net metering because it's very, very important. When you generate excess electricity, okay, instead of letting it go to waste, it goes to the grid. Now you need a meter to capture the amount of electricity that is going into the grid so that you can be paid appropriately for that, right? Now, here is another way to rate. Imagine that maybe you don't have enough storage or you have used up your storage and the sun refuses to shine, okay? Because you're connected to the grid, what that means that you can actually pick power from the grid. So it's the reverse. You're sending to the grid in the first instance, but this time you're collecting from the grid, okay? And you're using the same meter for that purpose, right? Now, what happens is that at the end of the month, the meter will now calculate who has collected more or who has given more. If you have given, for example, if you have given 20 kilowatt hour to the grid and you collected 25 kilowatt hours from the grid, then you are going to pay for the difference. That is for the remaining 5 kilowatt hour excess that you have collected from the grid. So that is why it is called net metering. It will do plus and minus, and they know who will balance who. That's why it is called net metering, and it's applicable for grid connected system. So
sorry before you go. So what piece of instrument does the analyst to see if you have excess and you need to give out, or if you have less and you need to take from the grid?
Okay, good. So it depends on the design of your solar PV system. One, you could design your solar PV system without batteries, and then you're connected to the grid. So what that means that anytime the sun is out, if maybe, for example, your house need for energy or for electricity, for example, is 5 kilowatts. 5 kilowatts is power, it's 5 kilowatt. At a certain time, your solar PV system is generating 10 kilowatts. So what I mean that 5 kilowatts you cannot use. It has to go into the grid because it's just connected continuously. You don't need any action to do that. It's automatic. The inverter does that, right? So it feeds it into the grid. And whenever it needs power, maybe for example at night, remember that we're talking about your system without a battery. So what happens at night? The sun is no longer there. So the inverter will just pick supply from the grid. It's automatic. It's done automatically by depending on the kind of inverter you have anyway. But this happens automatically.
Sorry, okay. I have a question.
Go ahead, please.
Sorry, I joined a bit late. So my first question is, we won't be able to get this material, maybe for personal review later?
Sure, you will. If she hasn't sent it already.
I've been sent to everybody, sir, unless you join late, sir. I've sent, what's the name?
Yeah,
sir?
My name is Stanley.
Okay, Stanley, I've sent, are you sure I've not sent, you've paid, I guess?
Yeah, I've paid, yes.
Please chat me on WhatsApp, I'll send to you, sir. Please, it's your right. In fact, you also get the video, sir. I don't know the training.
Okay, which number will I use for the WhatsApp?
Okay, I'll send it here on your chat box. Let me send it to you, sir. It's okay.
Okay, sir.
Go to chat box, sir. I'll continue, sir.
Okay, then the second question is, now, if you have, we're using the net metering. If you are feeding back to the grid, usually what we are feeding, either you are taking from the grid, we are giving back to the grid, is just voltage transmission. I don't know if I'm correct.
I don't understand what you mean by voltage transmission.
What I mean is that the grid supplies voltage. Now maybe you pick the voltage supply, now give it to your load, and maybe current is drawn. Now, if you are generating power, so in this case, you are sending back to the grid. So I'm asking, is it voltage you are sending back, or is it any other whatever you are sending back? So that's just my question.
Okay, thank you for the question. Now, what you're actually consuming, voltage, you don't consume voltage. What you consume is amperage.
Yes.
Yes. So voltage is the pressure that pushes the amperage that you consume. So what you're sending to the grid is the amperage and the voltage, of course. I mean, yes, voltage and is what you're pushing to. That. So voltage and amperage is voltage times amperage is what gives you power.
Okay, yes, that's correct.
Yes. So that's what you're sending to the grid, and that's what you're collecting back from the grid.
Okay, so it's the power we are sending, really?
Yes, it's power. Yes.
Okay.
Okay, thank you.
Hello.
Hello, sir.
Hello.
Hello.
Hello,
Please,
Suleiman.
Hello.
Go ahead,
Hello.
Suleiman. Suleiman.
Yeah. Okay. If you are, operating an on-grid solar panel, you want to convert from your inverter from the DC to AC, and you want to connect to the grid. Maybe the grid says 33 kV or 11 kV or low voltage, that's 415. Is there equipment that does that? Or there's a particular phase you must maintain a particular voltage? That's for your output to the grid.
Okay, so inverters comes with various categorization and spec. So you must get the right equipment to do that. Now there is not all inverters has that capability. You must go for the inverter that has the capability. And there is another thing I need to explain here. There's what we call anti-islanding mode. So the inverter should be able to sense when the grid has failed and not transmit to the grid. So if there's a grid failure, okay, your inverter should be able to send that there is failure in the grid and will now become unable to send that your solar power to the grid, because you cannot send that your solar power to the grid that has failed. I don't know if that's clear. So if the service may need to carry out maintenance service at a certain section of the grid, they will request for outage on the grid. Okay. When they request for outage, normally your inverter should be able to know that, look, there is an outage on that grid, and your inverter should not be able to send power to that grid. Otherwise, you induce power into the grid, which might be just abysmal, but it's not. It's wrong. It can damage, can cause a health safety problem. Okay. So now these are more technical involvement in all of this. But I just want us to understand this. Yes.
Hello, sir.
Yes, I can hear you.
Please, I just joined, not quite some minutes ago.
Don't worry. It's being recorded. It's being recorded, and you get the video.
The thing is that I don't know how you pay.
Okay, Engineer Uche, can you address that?
Hello.
Hello, can you hear me?
What's your name, sir?
Yeah,
What's your name? What's your name, sir? What's your name?
Adebisi is my name.
Adebiku?
Adebisi.
Okay, Adebisi. Okay, continue. I'll send you the information. Go ahead. Don't worry.
All right.
Just to continue the class. Yeah. Thank you, sir.
All right. Thank you.
Okay, no problem.
We are sending it to Adebisi. Can you
Someone is trying to say something, but the background noise wouldn't let me hear what he's saying.
Yeah, the background noise is
Gina Chima, can you unmute yourself, please? Gina Chima, can you unmute yourself?
Oh, okay. I've done that now. Okay.
Oh, can you hear me, please?
Yes,
I can hear you, sir.
I can hear you, sir. Go ahead, sir. Hello, I don't know who was trying to ask a question. Okay, go ahead, sir.
Can you hear me? Someone is muting me. I unmute and someone mutes me again.
Sorry about that. Sorry about that.
I said when you are sending the information to Adebisi,
yeah,
please send it to me as well. Lawal Abubakar.
I'll do that, sir. And I'll also send you the material, sir. I'm sorry. I'll do that.
Thank you very much.
Thank you. I appreciate you, sir. Continue.
Okay. All right. So now, still talking about the grid connected system, you remember I also mentioned about central PV systems, okay, where you generate from a central point in large capacity, and then you're feeding it into the grid. At this level, depending on your configuration, you could feed it to the 33 kV line and all of that. I know most of these connections can best be done at 33 kV lines. May not necessarily be done at 132 or higher voltage. So these are also known as solar farms. So when you hear solar farms, this is what they mean. Okay. or solar park or utility scale PV system. So large PV system, large scale PV power generation is concentrated at one specific location, such as plants. I mean, such plant can take up large areas of land and feed directly into the electricity grid. Now, the configuration of such plants is more comparable to conventional power plant. I think I've said this before. Producing three-phase power, they are connected to medium or high voltage transmission network. I think I've said all of this, so we can just proceed. So this is a schematic of a grid connected PV system. Okay, it comes from your solar panel, which is the first point that converts the solar energy into electricity. Then remember it's a DC power at this point, so you need to go to an inverter to change to AC power. Then you need an electricity meter to capture the amount of energy that is going into the grid. And of course, you need a fuse for protections and all of that before it goes into the grid. So this is just a simple configuration of a PV grid connected PV system. Now this one off-grid system. Okay. So this one off-grid system, PV system. Now they are not connected to the electricity grid. They are also called standalone PV system. Now the electricity is consumed very close to the location where it is generated, just like putting it on your roof and then you'll consume it, right there in your home. So off-grid system usually incorporates battery storage so that electricity can be supplied even when the sun is not shining. Solar water pumping systems are a major exception to this. Remember I told you that solar water pumping system, you don't necessarily need batteries on them. So they're just direct. Okay. So this is for an off-grid system. Now, off-grid systems are usually found at locations where there are no electricity grid available, like rural communities. Now, the system components differ from grid-connected system, and the array size is typically much smaller, especially for small off-grid applications like the solar home system. The common example that comes to mind is this empty yellow box. Now, these are typical off-grid applications, right? Now, the PV modules are connected. The PV modules are connected to charge controller. I've explained what charge controller does, which regulates the charging and discharging of the batteries. Otherwise, the battery will quickly spoil. So only DC power is supplied. You charge the batteries with DC power, not with an AC power. Now, this is just to throw more light into the off-grid systems, okay, where you have the generation just close to the point of consumptions, and then you need the charge controllers to control the batteries, because in this case you're going to have batteries. For the time the sun is not going to be shining, you need batteries to support the load. So many of these. Okay.
Engineer Shimana.
Yeah, I'm with you.
Please, for pumping water pumping this without a battery. Okay. So in the night, supposing you want to pump water, will you be able to work?
No, of course not. It will not be able to. Now, the reason why you don't need battery is to optimize the cost. Now, remember you can store water. All you need to do, have a storage tank during the day. Use all the sun to collect the water you can collect and then store in your tank, which becomes available for you at night. So your water storage is also a form of energy storage, in case you don't know. Okay. There's what we call pump hydro storage, where they generate power with hydro. Okay. When they have excess electricity, they use it to pump water to a height. Okay. So that when they need more electricity, they can discharge that water to turn turbines. Now, that's just by the way. But the point I'm trying to make here is for you to understand that water storage is also a form of energy storage. So you don't need to store that energy in batteries. Instead of storing them in battery, which is very expensive, store them in form of water that you're going to use at night.
Engineer Chima, can you spare me 1 minute also? Engineer Chilama, in Europe now, one of the challenge of batteries is large-scale storage. The world is here to come up with large-scale storage, except for research that Tesla and others are doing. In Europe, in Luxembourg, in some countries in Europe, what they do now is to use water to store energy. In Germany, at night, they have excess energy. In fact, sometimes they pay other countries to come and take energy because industries are not working. So what they now do is they do what they call pump storage system. Pump storage system simply means you have a huge reservoir uphill somewhere. So when you have those excess water, you use it to pump water up and store it at night. Then during the day, when there's shortage of electricity, you now turbine the water down. So that's exactly what Chima is saying. The idea of the pumping is for you to save energy. So somebody also asked that question again, Engineer Ibrahim. During the day, you pump the water, store it in the tank. During the night, there's no light, there's no radiation, it's not going to work. So water will come from the tank and then you use it for your daily use. So that technology, that concept is now being used in large-scale storage systems because we don't have large storage batteries, and pump storage is the future battery they are looking at. Thank you.
Hello, Engineer Uche.
Yes, sir.
Yeah, you know why I'm asking is that there are instances where some clients will want to have a solar system, backup batteries, because their pumps is pneumatic pumps, that booster pump.
Okay.
Rather than use gravity to supply water into the building, they use the pump. So, but in the case that you don't have a backup, I mean, it means the pump will not be working in the night.
True.
So that was.
So you have to go for battery. You have to go for battery.
Yes, your question is very valid. So in that case, please bear in mind that there is no one size fits all in this solar PV system. Okay, so it's on case by case basis. So for the case that you've situated now, yes, you have to make provisions for battery storage. If that booster pump have to work at night, okay, so they have to make provisions for storage to provide power for it.
And the energy consumption is very low, actually. So
yes,
I think it will work, but not like some of our submersible. Okay, I get it. It's possible. The requirement is not that much for those booster pumps.
Now, we are not saying that it is not possible to power those large submersible pumps with solar systems and battery. But like I said, the essence is for cost optimization. If the client want to pay the money, no problem, go ahead and do it and put the battery for the client. But I'm telling you that, I mean, depending on this situation, okay, of water need, right? If you're just pumping to a storage tank, okay, whereby you don't need that energy to redistribute that water. In the case of Mr. Tajin, the case you situated, you need is just a redistribution of that water to the facility, right? But whereby you just need to store that water at gravity to flow freely, over gravity, then you don't need those battery storage. But if the clients insist that they want it, you give them the quote and they'll pay for it. That's fine. It's still going to work.
Okay, thank you.
All right, thank you. So now we are still in the off-grid configuration. Now we have the micro and then the mini.
Sorry, the off-grid now, the short one, example is just like the solar system in our homes.
Yes.
Okay, sir.
Yes. So we have the micro and we have the mini grid. Okay. Now they're all basically small electricity grid providing electricity. Okay.
Please, I have a quick question.
Please go ahead.
There was something you called charge. Is it charger? Please go to the previous slide. Charger. No, not that one. PV combiner box. What does that do in that configuration?
Okay. PV combiner box. Now when the now you have different models, right? If you have the solar PV panels, you have different models on your roof, right? Now each of this model is coming to this PV. Now this PV combiner box is what combines the energy from these different models. I don't know if that's clear. You have energy, you have different models, different wire coming to this PV combiner box. So at the PV combiner box, it combines the energy from these different models and then push them through one wire into the charge controller.
So you mean it's like if you have like arrays of panel on your rooftop?
Strings.
Yeah, you have different strengths.
Strings, yeah.
Okay.
I will come to that. We'll go in. Now, this is just a diagrammatic view. We'll come to more details about this. Yes.
Okay.
Thank you. But just to give you an overview for the fact that you've asked now, I hope you understand what that means. So we have the micro and we have the mini grid. Now, these are basically small electricity grid providing electricity to, for example, a small island or a remote building complex or village and all of that. Now, these are smaller off-grid applications and all of that. So we'll talk about mini-grid. What that means simply means that it's a solar system that has its own distribution wires, the own distribution network. Okay, so you're generating and you have a mini distribution network to take that energy to people's home. That's what we call a mini grid and all of that. So in some cases, you could combine that with generator. In some cases, you could combine that with generator and batteries and all of that. So depending on what works best for you, when you do your financial modeling and all of that, whatever works best for you is what you adopt. So here, okay, I think I've explained this already. Now, electricity typically produced and stored at a central point from which it is distributed. I've done this explanation, so let's just proceed. So let us go into the components of a PV system. Okay. So let us start from the basic, the PV panels, the PV cells themselves. So selected technique. I think I need to mute it. Genoche, please help me mute everyone that's not speaking so that there's noise that's coming. If you're not speaking, just mute yourself.
Yeah, thank you so much.
Okay, so thank you. So we're going to start from the very basic of this solar PV cells. Okay, now selected technological characteristics of silicon wafer base and thin film. Now there are different kinds of PV cells, right? Now if you're looking at the screen, you're going to see that we have three different pictures. One of them is poly, one of them is poly PV, one of them is mono, and then one of them is thin film PV cell. Now they all have their own different characteristics. They have their own ups, they have their own downs. We are going to look at all of that. Okay. So, but just as a snapshot, if you look at the table from the first one that we have, which is the polycrystalline PV system, okay, or the SI wafer base. SI means silicon wafer base system. Okay, PV system.
Yeah, this is not there with you, but what's it called? The charger.
Daniel, you asked me a question. Okay, I think that's a mistake. So we now have also the silicon wafer base PV cell, which is monocrystalline in this case. Before we now have the thin film. Okay, so let us look at their panel efficiency. Okay, now what panel efficiency means is their ability to convert the sunlight falling on them into electricity. Okay, that's what we mean by their panel efficiency. Now for the poly, it can be up to 18%. For the mono, it can be up to 22%. Whereas for the thin film, it's about 17%, can be up to 17%. So if you look at that, something tells that, okay, mono is the best in terms of panel efficiency. But there's another side to it. Okay. Now there's what we call power temperature coefficient. Okay. Now temperature affects the efficiency of these panels. If you install these panels where you have a higher temperature, it reduces the efficiency. Okay. Now we also have to look at their ability to their tolerance, to these temperature changes. Okay. So now there's a classification known as the power temperature coefficient, right? So it can be the polycrystalline panel can achieve up to 18% efficiency at minus. Now, I think this slide should have come later, but let me just go. I'm going to try to explain this here. Like I said, temperature affects the efficiency of these cells. Okay, so there's what we call temperature coefficient. So the higher the temperature in the atmosphere where you install this PV system, the lower the voltage. It affects the voltage of the PV cell. But let me not go into that so I don't create confusion. There's a place to talk about it in more detail in a way that you can understand. But just ignore that middle line. I will talk about it later in the presentation. I don't want to create confusion. I don't want to lose your understanding on this. I'll come to that. So now let us look at the market share. Okay. Now, if you look at the market, you find out that the polycrystalline has the largest share of the market. Okay, as opposed to monocrystalline. But if you look at the efficiency, you would think that monocrystalline should have the higher market share because it's higher, the efficiency is higher, right? Now, here is the twist. The difference between this 18% and this 22%, the difference in cost is so much that it's negligible. That's the point. The difference in, let me repeat this. The difference in cost between this 18%, that is this polycrystalline panel, and this monocrystalline, which is 22%, the difference in cost is negligible. So people will just prefer to go for the polycrystalline. Because if you look at the cost of buying this one, for just difference of 6% efficiency, you just go for the poly. That's why it has a higher market share. Okay. Now, this was according to the research done by an independent body in Germany, Renewable. Okay. So maybe this might change over time, but as at the time they conducted this research, this is the result that they came up
with. Hello, engineer.
Okay, please go ahead.
Hello, engineer.
Yeah, go ahead.
Please, in summary, I just want to summarize this table. In summary, what we're trying to say now is that at a higher temperature, the efficiency of the poly drops a little compared to the mono. Is that what you are saying?
Oh, every one of the panel. Yes, can you hear me?
Yes, I'm hearing you now.
Yeah, the efficiency of every panel drops with higher increasing temperature. So, yes. But some are more tolerable than the others. So the
so the poly is more tolerable.
The thin film, yes, the thin film is the most is the highest in terms of tolerance. So if you want to store a solar PV system in a place that has a very high weather temperature, like the northern part of Nigeria that has a high weather temperature.
Okay, you go for thin film.
Thin film is better, yes, because it can tolerate this kind of temperatures. Yes.
So like we around the Niger Delta, which one is better?
No, you can go for poly or mono, whichever one you take is.
Okay, in the Niger Delta region.
Yes, yes.
Okay, thank you.
Then sorry, is it written on the panels if they are poly or mono or thin film, or how do you identify?
Yes,
it's written. It's written.
Okay, thank you.
Good afternoon, everybody.
Good afternoon, Christopher. Or who is speaking?
Charles speaking.
Okay, Charles.
Charles, yeah, I'm happy to be part of this training program. I really wanted to throw more light on this issue of power temperature coefficient. Yes. If I heard you right, you said that the cost between the poly and the mono is negligible in terms of cost.
Yes.
I don't know if I got that right.
When you look at what you're going to get, by that incremental cost of buying the mono, you will just want to.
I would have thought that since the cost is negligible, it would have been, then it's better for me to go for the mono. The cost.
No, the cost with respect to the difference in efficiency.
I think it's now you are clarifying.
Yeah. Yes.
Okay. Just to be sure that I understood it right.
So let me rephrase that statement. Not that the cost is negligible, but the efficiency gain is negligible. I hope I'm not confusing you now.
Yes, you are guys. It's now I'm understanding it better. You know, when you say you will treat it later, that's why you just talk.
Yeah.
It's now that I'm getting it clear.
Yeah. Thank you very much for bringing that up. Yeah. The efficiency gain compared to the cost is negligible.
Cost, it's not that the cost is negligible.
Exactly. Yeah. Okay. Thank you very much.
Thank you.
In other words, if we take it a little bit further, the mono
is more expensive
than the poly. Yes.
Poly, that's what you're trying to say in essence.
Yes. But if you check the difference, it's just 6%. Why go for that high? Okay, yeah, I get it.
Yes. Yeah. Thank you very much for bringing that up. It's clear. I will still come back to this power temperature coefficient. I mean, it's a technical part of solar PV system. So we'll get into that. That's why I didn't want to begin to go into it here now, so I don't create confusion. Okay, so now this is how you start the solar PV model. Now you start from the PV cells. Okay, when we talk about, most of us are very conversant and familiar with PV models, but that PV models that you have is a combination of PV cells. Okay, it has several numbers of PV cells. So if you look at the screen, you're going to see PV cells. You now combine them to form a PV module. Then you now combine PV modules to have a solar array. So this certain number of PV modules give you solar array. Okay, so this is just a basic classifications. Now, PV modules are formed by connecting PV cells in series or in parallel and encasing them in a protective material. Now, PV modules can be connected in series and or in parallel in order to form PV array. It's just the same thing I just explained. So the number of modules is determining the maximum power generation capacity of the PV plant. Okay. The number of PV modules you have. Now, when you see those PV modules, you're going to see their rated capacity in terms of kilowatts or watts. They all mean the same thing. They're all talking about power, either in kilowatt or watt. In most cases, it is in watts. Okay, so you're going to see their rating, okay, and all of that. Those ratings are ratings at standard test condition. Don't worry yourself, we'll come to that. There are dedicated slides for that. We'll come to that. Okay. But you're going to see a ratings on them, okay, that tells you the maximum amount of energy power it can generate. Okay. So now let's talk about inverters. Having talked about the PV cells and modules and arrays, let's talk about the inverters. Of course, we all know what the inverter does. An inverter converts direct current input from these PV panels, arrays, or from batteries. Batteries store energy in DC form. So even if you're getting the energy from the batteries or from the sun, the inverter does convert it to AC current, from direct current to AC current. That is just the work of an inverter. So, and it's just been depicted by the pictures that we have here. So you have the solar radiation, it goes through the PV array that converts it to a DC current. And this is an inverter that converts it to AC current before you feed it into the grid or into your homes for whatever use you want to use them for. So PV models produce only DC. That I explained this already. So now let us look at types of inverters. There are different kinds of inverters at different levels of design. Okay. So there are three different sizes of inverters. There are inverters that we call micro inverters. Micro inverters mean that every PV modules has their own inverter. So if you have 10 PV modules in your house, each one of them have their own inverter. And what this does is that as the PV module is generating electricity in DC, it is being converted to AC at the module level, at that each module level. Okay, so what is now feeding to the combiner box is what we now know as AC current instead of the DC, as the case was in the other instances that we gave. So micro inverters, which are directly connected to a PV module, e.g. up to maybe 300 watts, you connect an inverter. It's a small micro inverter you attach to every module. So it's not common. It's not common in Nigeria, even across the world. It's not common, but they have their own advantages as well. So let us look at strange inverters. Now, when you connect a certain number of PV modules to one single inverter, that inverter is known as strange inverter. Okay. Now, when you have certain number of PV modules, what you now call it is strange, right? So, for example, now if you have 20 PV modules and you connect 10 of them to one inverter, 10 PV modules to one inverter, then another 10 PV modules to one inverter, that is strange inverter. So that 10 forms a strange. The other 10 form another strange. You now connect them to each string to one inverter. That is strange inverter. So strange inverters which are connected to one or a few strings of PV modules. Such strange can have up to 20 modules. You can have 10, you can have 20, depending on the ratings of the inverter and the amount of solar PV power it can take.
Sorry, sir. Sorry to draw you back. Please just, I'm not getting you. This the strange inverters you're talking about.
Okay.
Is it that you say 10 modules to a different inverter, or the 10 modules to the same inverter, or rather 10 to the same inverter, one inverter?
Yes. 10 modules to one inverter, another 10 modules to one inverter.
So how do you conduct them through the charge controller?
How do you what?
And how do you not bring them together into one inverter?
So there's a combiner box that does that. That's the
okay,
combiner
box
box that someone was asking about the other time. Okay, so let's proceed.
I think, Shima, sorry, the one person that asked last question, string, when we say string, maybe we'll still get to there, is a collection of solar PV panels, maybe 3, 4, connected in either series or panel on one side. Then you have another string. So it's still going all into the combiner box, but they are coming in strings of 12, or strings of 20, depending on the voltage that you want. Maybe after the next slide, we'll get there. Tim, I can continue, please.
Okay, thank you. So now we have the central inverter. In central inverter, even if you have 1,000 PV modules, they are all connected to one inverter. It's huge, it's big. Okay, that's as the name implies, central is a central inverter. Okay, so I don't think this needs too much explanation. It is self-explanatory. Even from the name, it is very well self-explanatory. So now let's talk about the mounting structures. This is very important, and this is often overlooked by PV design, especially installers and all of that. And we will find out why it is important. Now, the fundamental requirement of mounting structures are that they must support the weight of the PV modules. They must distribute the load evenly onto the roof / the ground below, and they must withstand expected extra loading, e.g. from the wind or the snow. Mind you that these PV panels has weights, okay? And you're putting them on top of a roof. Now, it may not have been envisaged in the design of that structure that this roof was going to have such weight on the roof. So you need to, as an engineer, you need to be sure that whatever structure you're putting that panel, that the structure has the capability to withstand that weight, okay? So it's very important. Otherwise, you add extra load to a structure that you don't know the structural integrity, which can lead to engineering failure and all of that. So it's important we look into all of that. So since large array structure, including modules, are heavy, it is necessary to seek the advice of a structural engineer prior to roof mounting. I'll just explain this. Now, the structure should have optimum orientation and tilt angle to maximize power output, and all shading should be avoided. Now, the emphasis here is optimum orientation and tilt angle. I will explain that much later. Now, the structure will typically be made from aluminum or galvanized steel. Painted steel or wood are also options, though such structures will probably require more maintenance over the 20+ years lifetime of the system. Remember that this system will last for about 20 years plus. So if you're using wood, you should ask yourself if this wood can have a lifespan of up to 20 years. If not, then it requires maintenance, maybe periodic change and all of that. So now that is the downside of using wood and all that. So alternatively, it is advised that you use aluminum or galvanized steel that can have such a long lifespan and all of that. So let's talk about mounting structures. Still on mounting structures. Solar panels can be installed on fixed support or on a tracker. Now, you know that the sun does not stay one place. The sun moves. It rises in the east and sets in the west. Now, if you do your solar PV installations and it's facing the east, for example, when the sun has risen and it's about setting, which means it's going to be backing the sun, right? It might not be able to capture enough energy from the sun. So that has necessitated the need for trackers on solar PV, even though it is not common and it comes with an extra cost, additional cost. So when you're doing your analysis, you have to also check the cost of these trackers and then see if the extra energy you're going to get by putting that tracker is viable, is worthwhile, to spend that money on the tracker and all of that. So that's why it's important we do all of this analysis in our design stage to know what could be included in our design and all of that. So fixed support are most often directed towards the. Someone asking a question?
Yes, I want to ask a question.
Go ahead.
Please, can you talk further on these trackers? This tracker, Is it for concentration of the solar energy or what, please?
Yes. So it can follow the sun. The tracker, what the tracker does, it follows the sun. So the sun rises in the east. As it's moving toward the west, the tracker is moving the solar panels to keep following the sun, so it can harness the maximum amount of energy it can from the sun at every point in time. That's the purpose of the tracker. Okay, I hope that's clear. So,
hello, Engineer Chima.
Yes, please.
So, which is the best position to direct the panel?
We'll come to that. We're going to come to that.
Okay.
Thank you. All right, thank you. So, fixed support are most often directed towards the south in the northern hemisphere and vice versa. So, this is just the question you're asking. Okay. If you want to do a fix, of course, like I said, the tracker is not very wrong, because when you look at the cost benefits, it might not be very viable, right? So now, if you want to do a fixed support system, how do you now position it so that you can still maximize the energy from the sun, right? That's the question that you're asking. So now, the fixed support are most often directed towards the south in the northern hemisphere. So now, when you look at the, for those of us that understand our geography or that still remember our geography, there is a northern hemisphere, there is a southern hemisphere. I think in the next slide, I think I have a diagram to illustrate that, to make it clear to every one of us. But just as an introduction or as a rule of thumb, right? If the location of your installation is in the north, the northern hemisphere, your solar system should face the southern part of the hemisphere, of the equator, right? If you're in the northern, if you're in the southern hemisphere, your solar system should face northern part of the equator. We'll come to that. Don't worry. There's a diagram that helps us to understand it. Okay, but essentially, I want you to understand that trackers, the importance of having trackers. Yeah, even though it's not common, but you need to have that knowledge. The reason why we have trackers to follow the sun. So trackers are motorized structures that follow the path of the sun. Simple. Okay, so this is just also trying to now trackers. There are two different kinds of trackers. We have the single axis trackers and we have the two axis trackers. The single axis tracker move only in one direction, from east to west, as the case may be. But the double axis trackers move in both in four directions, from east to west, north to south, in four directions. So let's look at the physical aspect of a PV system. Okay. Now, the PV system, the way we see it, we look at it as just a simple technology, but there is more.
Sorry, are we going to come back to positioning of?
Yes.
Okay. So let me leave it for them then.
Yes, please. So we'll come back to that. So PV systems, the way we look at it, because it's a hardware product, we see it as simple as it is. But beyond that, as engineers or as solar technicians or as solar installers, we need to understand the nitty-gritty of this PV system that we install or that we design. Okay, what are the conditions that makes it perform optimally, and what are the conditions that makes it perform suboptimally? Okay, so that's the essence of this this few slides that we're going to be talking about now. Okay, so the electrical power the electrical power P for DC system measured in watts is the product of voltage measured in volts and current I measured in amperes. I've stated this before, that power is a product of voltage times current. I want us to keep this in mind. Power is equal to voltage times current. So what this means that if current is zero, what is going to be power? Can somebody just comment on? If current is zero, what is going to be the power?
Zero.
It will be zero.
Perfect. And if voltage is zero, no matter the amount of amperage that you have, the power will be zero, right? So let us keep this equation in mind, because it's going to be very useful in the conversations we're going to have following. So under normal sunlight condition, the the PV cell's voltage remains fairly constant. So what this is saying, under normal sunlight condition, the voltage hardly changes. The voltage hardly. So once the sun comes up till the sun sets, even when the sun, even when there is a shadow or the sun comes down a little bit, the voltage hardly changes. Okay. Now, however, the cell's current is very sensitive to sunlight intensity. Now, the emphasis here is on current and sunlight intensity. So if the higher the sunlight intensity, the higher the current. The lower the sunlight intensity, the lower the current. And the lower the current, the lower the power output. Look at our equation. If current becomes lower, the voltage remains fairly constant, but the current is lower. What happened? The power is also lowered.
It will be lower.
Yes, if the current increases, now keeping voltage constant, if the power increases, if the amperage increases, the power also increases. I want us to understand this so that, because we are going to go a lot deeper into this so that you don't get confused. Okay, please, if you lose any point at this level, please let me know. Okay. So now let's take it further. Now, higher solar irradiance will produce a higher electrical current. Amperage is current, take note. So if you have a higher current, then you have higher power output, keeping the voltage constant. Now, low solar irradiance will produce a low electrical current. Now, so the surface area of the PV cells also affects the electric current output. So if you have a larger PV cells, of course, common sense tells us that you're going to have a larger electricity output. And if you have a smaller PV system, PV arrays or PV solar models, you're also going to have a lower electrical output. So the surface area determines the amount of energy you're going to get out of the system. Now, a cell with a large surface area will produce more electric current than a cell with a small surface area. So what this is saying in essential is that the surface area of your PV system determines the amount of electricity you're going to get, whether higher electricity or lower electricity. Okay. So those two main factors. And Ushe, please, okay. Can you help me mute everyone from some background noises? So those two main factors that affect the output of a PV cells are the intensity of the sunlight falling on it, and then two, the size of the cell. Okay. Now, other factors are also important and will be discussed, later. So, okay. Okay, so now there's a graph for us to go into more detailed analysis of the P is equal to voltage times current. Okay, so we call this the electrical characteristics and the IV curve. IV curve. IV means current voltage curve. Okay, now the current voltage curve describes an important electrical characteristics of a PV cell. At any given time, a PV cell is operating with a specific current and voltage, which lies along its IV curve, which is the red line. So if you look at the red line in the chart, okay, that is the power output from a PV cell, okay. If you look at, okay, I think let me just go ahead. I will explain this diagram later, but let me just run through the write-offs. Then I'll come back to explain the diagram. So this line shows the current which is produced over a range of voltage. Okay, now let us look at the red line, please. This red line here, okay? This is the amount of electricity that is produced from the PV cell. Now, on the vertical axis, you have the current. On the horizontal axis, you have the voltage. Now, remember that the combination of these two is what gives you the output of the cell, of the PV, that is power. Now, if you look at this line, this red line, if you're standing at this very point, okay, what is your voltage at this point? Can somebody unmute and speak out to them? At this very point, what is the value of your voltage?
Zero.
Zero.
Okay. What is the value of your current? It's maximum. Your current is at maximum. But at least so much as your voltage is zero, your power is what? Zero. Okay. Okay. Now, we are talking about the current. Remember that when the sun is high, okay, you have a higher current that is coming out. But when the sun reduces, this current also reduces. Just keep that in mind. Now let us come to this end. If you're standing at this very end, your current becomes zero, but your voltage is maximum. And once your current is zero, your power output becomes zero. Okay. So we don't want to be here. We don't also want to be here. So at this point, the current is maximum, but the voltage is zero. At this point, the voltage is maximum, but the current is zero. So we need to find a way to balance it. Okay. We need a way where we can have the maximum product. So essentially, what this is trying to say, what combination of voltage and current can we have along this red line that will give us the maximum power output from this chart? Okay? And any point where we can get the maximum value of P, that's what we call the maximum power point, right? That's what we call MPP, right? I hope, so yes, that's what it is. The MPP, that's the maximum power point along the red line. Okay. So now, what is going to happen is this: we have to move along this red line. At this red line, as you keep moving, the current is still maximum. Okay, but the voltage is no longer at this point. The current is maximum, but the voltage is no longer zero. But if we keep moving, the voltage keep on increasing, meaning that our power will keep on also increasing because the current is almost constant. We keep increasing the voltage, but as we keep moving, at a point, the power, the current begins to drop. Sorry, let me get, okay. So as you keep moving, the current begins to drop, okay? But the voltage also keeps moving, towards the maximum point, okay? So there's a point where we get the current will keep dropping significantly, which is from this point now, the current will now begin to drop significantly. So if you keep moving from here, the current will begin to depreciate the power output that you're going to get. Okay? So just somewhere around this place is where you have the maximum. This is where you have the maximum power output. This is where you at this point you maximize the current, you also maximize the voltage to get the maximum power output. So here it's where we have our maximum power output. I'll come back to this. Let me just read through the write-up. So now this red, the red line that I just explained. Okay.
What if you move a bit closer to the left, instead of that point where we have the optimum point? If we move a bit to the left, don't you think we also have optimum power there?
Now, if you move a bit to the left, so you will find out that your current will increase or decrease marginally, but your voltage will reduce almost significantly. You understand? If you move to a bit to the left, your power will increase maybe slightly, but your voltage will reduce. If you move to the right, your current will reduce, your voltage will increase.
I think it's very clear in the diagram because if you look at the arrows, the one pointing to the left and one pointing downwards.
Yeah.
If you use the arrows, you see it. What is the distance between the red line and the arrow at the bottom? You see it's marginal.
Yeah.
If you look at the arrow pointing downwards and the red line in case of the voltage, you see it's very significant. So if you end at 10 for it to move further to the left, you are decreasing the voltage significantly. but the gain in current is very marginal.
Yeah.
And therefore, you are losing a lot of power output.
Also, can I just chip in this? Somebody who is coming from the water angle. This is more like also pump curve. If you remember pump curve, two things influences your pump: the flow and the head. If you go to buy a pump, two factors is what you're looking at: the flow, which is in this case is like the current, and then the head, which is the pressure, which is the voltage. Now, if you want your pump to last long, number one, and if you want your pump to be optimized, that is where you now have what we call operating points of the pump curve. Those are mechanical engineers will be at home with this. Now, the implication is this: you can get a higher head, but the flow will be so small. You can get a higher flow, but the head will be small. So you will now know which one do you prefer, and at what point. But for in case of some of these appliances, not playing with the voltage, fixing the voltage is more important. I don't know if I'm making sense.
Yeah,
fixing the voltage, because your appliances is rated based on 48 volts, 12 volts. Batteries are 12 volts or 48 volts or 24 volts. So you need to fix one variable and then make one inflexible. And you need to fix one boundary condition and then the other one, because so which one is more important? So for pump that we use to pump water, the most important variable most times is the head. The capacity to be able to deliver that head. Then the current, which is not the flow. Okay, let's say instead of this tank filling in 1 hour, okay, let it fill in 2 hours. Who cares? But the worst case is that it's not able to deliver water at the depth of a borehole. Thank you.
Okay, thank you, Generation. So I'm glad that we understand this now. Okay, so the line shows the current I, which is produced over a range of voltages. And now this current is represented in with the short form of SC, that is short circuit. I subscript SC, right, represent the short circuit. That is ISC is represented, is used to represent a short circuit current. Yeah, so that is the value at which the current is at maximum and the voltage is at 0. Remember, I asked you this question, where the current is at maximum. Now look at it here. At this point, the current is at maximum, but the voltage is 0. So at this point, the current is that is short circuit current. That is the current at no flow. The current at 0 voltage. That is short circuit current. Okay. So now we have the open circuit voltage, which is the VOC. Okay. Now VOC is the voltage at this level, where you have the voltage at maximum, but current is 0. Okay. This is what I explained earlier. So this is
up and down.
So this is VOC, right? And this is ISC.
Immediately off, everything become calm. No, I am in for another lecture, but he was interrupting.
So now I have explained this power curve, but let me just read through it. Okay. Now the power curve, which is the blue line. Now this red line is the voltage and the current curve. Okay. So the power curve is this blue line that we're now looking at. So this blue line is showing us the combination of voltage and current at every point along this red line. Okay, so you find out that it started from 0, it started moving up until this is where it's the maximum. And that's where we have the maximum power point here. So it's got to the maximum. If at this point, remember like we explained, if you move away from this point, the power begins to decline, either left or right, whichever way you move, the power begins to decline. So this is where you have the maximum power, right? And that's why when you see some inverters, they will say that it's an MPPT, okay, maximum power point inverter, tracking and all of that. So it's a maximum power point tracking. It has that feature, okay? So that's the meaning of MPPT. So the power curve of the PV cell is shown by the blue line, like I explained. Now, this line shows the electric power produced over a range of voltages under normal operating condition. Okay, now under a normal operating condition, the curve grows and contracts along both the current and voltage axis. Now, the maximum power point, MPP, is the point at which the cell produces the maximum power, and it occurs at the knee of the power curve where the product of voltage and current are greatest. Remember, the product, power is a product of current and voltage. So where this product is greatest, that is the maximum power point. Okay. So the maximum power point is thus, that is P maximum power, that is where the maximum power is generated, which is at this point, it is equal to maximum power point of the voltage times maximum power point of the current. So at this point, the current at this point is called current at the maximum power point. The voltage at this point is called voltage at the maximum power point at this very point. But if you move towards to this direction, the current at this point is called the short circuit current. And I want us to remember this definition, that short circuit current is the maximum current when the voltage is 0, whereas the open circuit voltage, which is at this point, is the maximum voltage when current is 0. Then we also have the maximum power point, which is here. Okay, and at this place you have.
Nachima, can you come again? You said okay. The short circuit
voltage. Okay, no, short circuit current.
Current, yeah. It's when the voltage is 0 or current.
When the voltage is 0 at maximum current.
Current. Okay, and here is when the current is 0 at maximum voltage.
Yes, that is VOC, open circuit voltage.
Yeah.
Okay. So we're in order. So now let us look at other factors that are affecting power output. We've discussed about the solar array. I mean, the size of the the area of the array, like the area of the solar panels. We've talked about that, and we also talked about the intensity of the sunlight. Now, let us look at other factors that affects the solar PV output. So, electrical characteristics and the IV curve. So, there are 3 critical factors which affect the instantaneous output of PV cells or modules. One of them is the solar irradiance, incidence on the surface, that we've discussed, the intensity of the sun. Now, another one is the temperature of the PV cells. The temperature of the PV cells affects the output of the panels. And again, the third one is the electrical load resistance connected to the PV cell. These are the 3 key factors that affect the IV curve, essentially. So let us look at the importance of the irradiance. Okay. Now, the output power of a PV cell or PV module directly depend on the solar irradiance incident on the surface. As irradiance G increases, the current I increases due to an increase in the level of photoelectric effects. Right? Now let us look at this graph. Now this is different time of the day. This is when there is the moon, the sun is not out. This is when the sun is out. This is when the sun is at peak. Okay. If you remember what I told you previously, I told that the voltage is almost constant. Okay, when the sun comes out or there is visible sunlight, the voltage is almost constant. But what keeps changing is the current, which is dependent on the intensity of the sun. So the sun comes out more, the more the current increases. So if it's been depicted in this graph, you find out that even at when the sun is not out, but the day has broken, you find out that the voltage, now this is the voltage, it does not really change much. Now this is when now look at the level when it was, when the sun has not come out. Now when the sun is at maximum, look at where it is. You find out it has not really changed much. But look at the current. Look at how significant the change in the current is. Okay. Yeah. So That is to tell you how the incident, the solar intensity, the amount of sunlight falling on the panel, that is to tell you how it affects the output from the solar PV, okay? So one of the major things is the intensity of the sun. So now the voltage output, on the other hand, varies only slightly with changing irradiance that I've explained already. Now this means that as soon as the sun illuminates the surface of the cells or the model, the voltage rises to a value that is close to open circuit voltage. Okay, once the sun is, you remember that at this point, we have our open circuit voltage. So once the sun comes out, the voltage is also just go close to that open circuit voltage, right? That's what it's saying. So regardless of the change in solar irradiance, such as shadings from passing cloud, the voltage will fluctuate only slightly below that open circuit range. I hope this is clear. Any question, please feel free to ask. So the current is not the same. However,
sorry, Mr. Shima, before you leave the voltage, so typically your solar cells, do they come in different voltages, or typically they are all produced at a particular voltage?
When you look at the label in your solar panel, you will see the voltage. They all have their operating voltages.
Okay, so which means the different solar panels come in with different voltages?
Yeah, it's possible, yes.
Yeah,
okay.
Typically 12, typically 24, 48. You can string together too.
Yeah, to get the required voltage that you want, you can string
string together. If you string two in parallel, you get just like what we do in school, our what do you call it?
Yeah, I understand that part. Okay, just to know if they are all in maybe 2 volts and you have to string them to get your voltage.
It's 12, or it's 24. They come in 24, 48.
Usually come maybe 12, 24, 48, and that range, you know. Yes.
Okay.
In multiples.
Okay. I think the last speaker question was, is it that each and every cell have? Oh, I thought that was his own. I thought he said it does it mean that each and every cell have voltage?
Okay. Thank you for that clarification. Now, when you combine these cells in a model, okay,
yes,
depending on the voltage of the model that you want, every cell has their own voltage. So it's how you combine these cells in the model that determines the overall voltage of the model. I don't know if you understand. So if you want the model to output 12 volts, you combine the cells in parallel until you have 12. Then you now keep combining in series until you fill the entire model that you want. I don't know if that's clear. I don't want to go into too much of the technicalities so that some of us that are not so technically inclined are not lost in the process.
Yeah.
So
hello.
Hello.
Yes, okay.
Please, the cell arrangement, I think that is from the manufacturer.
Yes.
You buy the models, yes.
Yes, okay. that's I don't want to go, but that is left for the manufacturer. So where you as a project developer, please just look at the voltage, that the nameplate voltage, then you know how you combine the models. But if you're talking about the cell level, that's left for the manufacturers. Okay. Yes. So thank you. Now, the current, however, is like I explained for the voltage, that once the sun comes out, the voltage just moves close to the open circuit voltage, okay? And irrespective of the passing cloud or whatever, it does not really change much, okay? But it's not the same thing with the current. So how the current, however, will increase in direct proportion to the irradiance, only reaching the module's full current under strong irradiance, such as 1 kilowatts per meter square. So so for this reason, current produced by the photovoltaic effect in a PV cell is referred. Please mute everyone for me again. Okay, so for this reason, current produced by the photovoltaic effect in a PV cell is referred to as photocurrent. Of course, you know that with the increasing sun, the current increases. So that's just the combination of the name, the current and the sun, which is the photo and all of that. So now, passing cloud or people which cast shadow on the PV models will cause a drop in current output. Remember that for the voltage, when there is a passing cloud or when someone is passing and casts a shadow on that PV model, it does not really affect the voltage. But in the case of a current, if somebody is passing, so for example, for a ground-mounted solar PV system, it is possible that maybe somebody could pass, or and then you cast a shadow on that solar PV model. For that moment that you're casting a shadow on that PV model, your current will drop, and once your current drop, your power output will also drop. That's what this is just trying to say in essence. Now let us look at the impact of temperature. Now we've looked at the impact of irradiance. Okay. Now let us look at the impact of temperature. Now this year we're going to talk about the temperature coefficients that I tried to talk about the other time, and I didn't want to go into full detail there. Okay. So now let's look at the impact of temperature. If you're not speaking, please kindly mute yourself so that you don't distract our conversations. Now, the performance of PV cells also varies with temperature, since PV cells and modules cannot convert 100% of the absorbed light into usable electricity. Some of this energy is lost in the form of heat, which causes the temperature of the cells to increase. Now, this is a normal part of the operation of a PV cell and cannot be avoided. Now, what is saying, not all the sun that falls on the surface of that solar PV system is converted to electricity. Some of them convert to heat, and they heat up the surface of that PV system. And once it's being heated up, it affects the output, the electricity output of that PV system. Now, as the PV cells get hot, its power output drops. This is because the open circuit voltage decreases significantly when the internal cell temperature rises. Now, let us look at it in the diagram. Now, this is voltage, right? At this horizontal axis. Now, this is current. Now, along this path, you're going to see different temperatures. This is 75 degrees centigrade. This is 50 degrees centigrade. This is 25. This is 0. This is minus 25. You can see how this temperature variation is affecting the change in voltage. So change in temperature affects voltage, while change in solar irradiation affects current. So any of these two can affect the output of your solar PV model. Okay. So we can see how significant this performance of this PV model has changed from minus 25 degrees centigrade to plus 75 degrees centigrade. It is significant. Okay, so with the increase in temperature, the voltage drops. And when the voltage drops, the power output drops. Now, under normal condition, the PV cells will always operate at a temperature higher than the ambient temperature. Is someone want to ask a question?
Yes, please.
Okay, please, go ahead.
I'm not clear with this this particular temperature-dependent IV curve.
Okay.
Because I don't know the UMPP range. I don't know how the voltage is moving. Is it moving along the horizontal axis or what?
Yes.
Because at
yes.
Towards minus 25 degrees C, I would expect that's an increase in voltage.
Yes, yes, there's an increase
while
in voltage.
At T25 75, it moves, shifts backwards.
Yeah, it decreases. Yes, yes.
So how is the temperature now affecting the increase in temperature? How is it now affecting the
power output?
The cells? Yes.
Is it how it's affecting the cell or how it's affecting the power output?
What how it's affecting the cells, I think, will determine the power output. But okay, let's say how it's affecting the power output.
Yes. So once your
can I draw his attention to the fact that there's a baseline.
It lowers the voltage.
There's zero. Yeah, there's a zero, sir. Engineer Lawa, there's a zero. So it means if you move to the right of, if you move to the left, yeah, is getting lower. So if here is 0.
Yes, the voltage is getting lower.
At high temperature. At high temperature, yes.
So at high temperature, the voltage is supposed to drop.
Yes, and it's dropping. It's moving back. It's moving towards 0, sir. It's moving towards 0.
Okay.
From a baseline of T0, yeah. It's moving. It's not moving towards 0. Yeah, we are saying the same thing. Yeah,
so
look at the rate. Yeah.
So remember that power is equal to voltage times current. So if your voltage is dropping and your current is almost constant, if you look at here, you find out that among these temperature changes, your current is almost constant. It doesn't change much. It varies a little. So if your voltage is changing greatly, it also then your power output will drop.
It's okay then.
Okay, thank you. So under normal condition,
sorry, my own question would be, when we're talking of increase in temperature, are we talking of the ambient temperature around the area or the temperature of the
surface temperature of the panel?
Okay, of the panel itself.
Yes. And that's why we said that under normal condition, the PV cell will always operate at a temperature higher than the ambient temperature. So if the ambient temperature, which is the temperature of the air surrounding that PV system, if the ambient temperature is, for example, 25 degrees centigrade, then the temperature of the surface temperature of the panel would be higher than that 25 degrees centigrade.
And the ambient is also as a result of the intensity of the sun. So I'm trying to get the irradiance and the temperature, because we're having the sun irradiance increasing and improving our current, and the same sun
is affecting your voltage.
It's affecting my voltage. I try to get the balance here now.
Yeah. So there are some certain locations where this the sun might be out, but the temperature might not be so high. That in some locations, right? Whereas in some other location, the sun can be out and the temperature will be high as well. So it's always best if where you have the sun, but it doesn't so much affect the temperature of the area. So if you go down to the south part of the Nigeria, the sun will be out hot. I mean, it will be out very well, but the temperature will not be as hot as it would be if you were in the north, maybe Borno or somewhere else in that region. Okay.
Hello.
Hello.
Hello. This is Usman Ahmed, engineer Usman Ahmed. Yes, you're talking about striking a balance between the two. And if you're in the northern hemisphere, I think there should be a way out to manage the hot intensity of the north in order to get the optimal best.
That's why you have to consider the right tool. So you use thin film solar panels are more adaptable for those regions.
Thank you.
Hello. I wanted to ask that the temperature.
Hello, did you mute yourself?
No.
Unmute yourself. We can't hear you. Suleiman, you're speaking, right? Unmute yourself so we can hear you.
We lost him. Go ahead, continue.
Okay.
Now, Chima, maybe we need to speed up a bit. I don't know, since we have a lot to cover.
Yeah. So an electrical load connected to a PV module will determine the points on the PV module on the PV module's IV curve where the module will operate. An electrical load could be light bulb, a pump, a grid or a battery. If there is less sunlight available, then the load will pull less current. Okay. So the voltage across the load and the amount of current that the load pulls from the module is determined for a given irradiance, and therefore for a given IV curve, the equation is this. Now this is Ohm's law. Okay, current is equal to voltage times. Now what we are trying to establish here is to establish the relationship how the resistance of the load also affects the output of the PV module. That's what we're trying to establish, and we are going to do that using the Ohm's law. Okay, we know that Ohm's law is equals current is equal to voltage over resistance. right? So where I is the current in amperage, V is voltage in volt, and R is the resistance. Now, if you look at that resistance, okay, if you have a load with a higher resistance, it affects your current, okay, and your voltage. Now, this current and the voltage is the current and voltage that the load is expected to draw from that solar panel, right? So what this helps us to establish is that is the relationship between voltage, current, and resistance at the load level. Okay, this is not mainstream, but I just felt that we should also have an idea that the resistance of the load that you're putting on that solar panel also somehow has a way of affecting its output. Okay. So note about batteries. If batteries are connected to PV modules, as in an off-grid system, the batteries will determine the voltage at which the PV modules operate. The module's output current will then correspond to the module's IV curve at that voltage. Now, what this is trying to say in essence that the load that you give to the PV module will actually determine the voltage at which that PV module will operate along the IV curve. Remember, we're talking about MPPT. That's why when you see some certain inverters, if you want to buy inverter, you will see something like labeling where they will say is an MPPT charge controller, right? That is for charge control that charges your battery. Now, what that means is that it optimizes, it kind of optimizes, it tracks the maximum point where you're going to get the highest power output from that panel, okay, for whatever load, maybe for charging your battery or for the load that you want to power. This might sound a bit vague, but the point I'm trying to make is to make you understand the reason why you see MPPT on some certain charge controller or some certain inverter, because now some inverters are now building charge controllers inside them. So you will see some certain levels, MPPT. So it's good to understand what this is mean and what it does. So when you see those MPPT, what it means that inverter or the charge controller has the capability to track IV curve, the IV curve that we discussed. So it has the capability to determine the maximum point where the maximum power will be generated from any solar panel that is connected to. That's what MPPT means. So in the event you have batteries that are connected to those inverters, those batteries becomes the load, and the battery will determine the point where that maximum power point is going to be. So let us move ahead. We need to quickly move so we can cover up what we need to talk about. So there's what we call standard test condition, okay? Now, due to the variability of power output of PV cells, depending on the parameter such as irradiance and temperature, like we discussed, the performance of different cells operating under different conditions cannot be compared easily. So if somebody is using a solar panel in Germany, remember they have different solar irradiance, they have different temperature, and someone is using a solar panel in Nigeria, we have a different weather condition. How do you compare these two, the performance of these two solar systems? Because the weather idea is different from our weather, okay? So this difference in weather condition now brings about what we now call standard test condition. Standard test condition. So at the standard test condition, they use a certain temperature, they use a certain sun irradiance to test the performance of that solar panel, okay? And the performance that you see at the level, like when you buy a solar PV module, you see the wattage. If it's rated 300 watts, that 300 watts is at standard test condition. So we're going to look at what they mean by standard test condition. What temperature is the standard test condition? What irradiance is standard test condition? So that's what we are going to talk about now. So in order to enable meaningful comparison between PV cells, the rated output of a cell or module is always measured under specific conditions. Now, these conditions are standardized across all testing facilities worldwide and are called standard test conditions. I explained this. So what are the parameters of standard test condition? One of them is the light spectrum. So the light spectrum is 1.5. We have the irradiance, which is 1,000 watts per meter squared. They will have the cell temperature. So these cells are tested at 25 degrees centigrade. So if you move above 25 degrees centigrade, if it's rated, if you have a panel that's rated 300 watts, and you're operating it above 25 degrees centigrade, for every degree centigrade that you move above 25, there is a corresponding loss of voltage. So if you're moving above 25, your power output is dropping. If you're operating it below 25 degrees centigrade, then you're increasing your power output. That's what it means. So each finished PV cells of PV module leaving the production line undergoes a flash test. It is exposed to a flash of light under careful control of the standard test condition parameters, lasting only milliseconds, and the output performance is recorded, and that's what you see in the nameplate of your PV modules. So subsequently, the cells or modules are sorted and sold according to their rated power. Now, the rated power is measured in units of watts peak. Okay, so if you see a solar PV module and it's rated 300 watts, it is the highest amount of power it can get under standard test condition. Under standard test condition, that's how they rate them. So, or kilowatt peak, and refers to the rated power on, I said it, under standard test condition. So let us look at the temperature coefficient. This is what I said they were going to come to back. I don't want to create confusion at that initial stage because there's a full slide for it. So now the temperature coefficient shows how voltage, current, or power output of a PV cell or module changes with changing temperature. Okay, remember that at different temperatures, their performance are never the same. Okay, so how do they change? So module data sheet gives temperature coefficient, that is TC, that is temperature coefficient for open circuit voltage. Remember that open circuit voltage is the voltage, is when the power curve is at maximum voltage, but the current is at 0. Okay, under standard test condition. So short circuit current under standard test condition and power at maximum power point. Okay, I want us to get used to this these abbreviations PMPP. This means that it's power output at the maximum power point. So when we see ICS, this is short circuit current, and when we see VOC, it means open circuit voltage, and I have defined what distance means. Okay, it's important we remember what they mean, even though you might not fully grasp it now, but over time you get to become familiar with them, and it's very, very important. So the voltage temperature coefficient is the most common one used, in terms of looking at the performance of solar PV systems. Now, inverters and other devices such as charge controllers can be damaged by modules or strange voltage that exceed the specified input voltage. The specified input voltages of these inverters or modules or string, as the case may be. Then conversely, if the voltage is too low, this can cause system underperformance. So let us look more critically into voltage temperature coefficients. So voltage temperature coefficients are given in the form of, for example, minus 0.156 voltage per degree centigrade. So what this means that for every degree centigrade rise in temperature, your voltage loss is minus 0.156. That's what it means. For every 1 degree centigrade rise in temperature, you lose 0.156 volt. But however, if you reduce the temperature, I must state that the reference temperature here is the temperature at standard test condition, which is 25 degrees centigrade. So if you move higher from 25 degrees centigrade, you lose this amount of voltage. Please, I hope I'm not confusing anyone. If you're getting lost, please call my attention and I will explain. Okay. Otherwise, I will assume that we are all flowing with what I'm saying. So the reference temperature, like I said, is 25 degrees centigrade. If you have 26 degrees centigrade, you're going to lose this 0.156 voltage. If you go to 27, you're going to lose this times 2. If you go to 28, you're going to lose this times 3. But if you move below 25 degrees centigrade, if you go to 25, 24, you're going to get, this will become plus. Your voltage will increase by this value. Okay, so when you see temperature coefficient of minus 0.156 volt times, per current, per degree centigrade, I want you to understand what it means. That's the essence of this. So now there's also current temperature coefficients. But like I said, the most common one that is being used is voltage temperature coefficient. But I want you to also know that increase in temperature also affects the current, but it is negligible. Okay, it's very, very negligible. So we don't really consider it. So for example, okay, look at what we have here now. For every degree rise in temperature, okay, you're only gaining. Now you're getting, for the rise in temperature, you're getting, but what you're getting is negligible, is insignificant. For every rise in temperature, you're getting 0.0029. Look at that. But for that same rise in temperature, you're losing 0.16 volts, whereas you're only getting 0.0029, which is negligible. Okay, so we focus more on this voltage because it affects the performance of that solar panel significantly. Okay. So there's also what we call the power temperature coefficient. Of course, if you've taken care of the voltage coefficient and the current temperature coefficient, then you will have also taken care of the power temperature coefficient, right? Because the power is a product of voltage and current. But however, this is what it means. For every rise in temperature, okay, for every degree rise in temperature above the standard test condition, you are losing 0.42 watts on that panel. You see how significant it is. And this significance is coming from the voltage, not from the current. It's coming from the voltage. So this is just a little calculation exercise. Assume the following data: a yearly daytime temperature at a location ranges from minus, now this, okay, this is minus 10 degrees centigrade to plus 45 degrees centigrade. A PV model is being installed, which has the following characteristics. You have the open circuit voltage of 43, of course, at standard test condition. Then you have the maximum power point voltage at 35.35, and of course, now these are just the characteristics. These are the data that you have been given. And now the question is, at temperature coefficient of this. Okay.
Hello, sir.
Yeah, go ahead.
Please, before you continue, I don't need a little clarification between this VOC and VMPP.
Okay.
When you were explaining my internet, my system went off, so I didn't really get it clear. Please, sorry for dragging people back.
No,
VOC and the VMPP.
No.
Thank you.
No, the VOC. Oh, wow. I need to go back. If I need to show you the diagram, I need to go back on many slides. But let me just explain from here, please. Yeah. So the VOC means open circuit voltage. Open circuit voltage is a voltage is on the chart that I showed previously. It's the maximum voltage, okay, that you have, but at zero current. Okay. You have a maximum voltage, but the current is zero. That's your VOC. Okay.
Can I also define it as the maximum as the voltage at no load?
Correct.
When no load is collected, I think it's the same thing.
Yeah.
Okay.
Yeah. It's the maximum voltage, but there's no load. There's no load on it. Perfect. Good.
No load.
Yeah. Whereas the maximum power point voltage is the voltage at the maximum power output of that panel. Is that clear? So your maximum power point, the voltage at your maximum power point will always be less than your VOC. I hope that's clear. Your voltage at maximum power, will always be less than your VOC. Yeah. Okay. So a temperature coefficient, now you're given a temperature coefficient. Now, this temperature coefficient that you see that for every degree rise in temperature above the standard test condition, which is 25, you're going to lose 0.168636 volts. That's what this means. Okay, so there's a note here. Temperature coefficient, which is the TC at the maximum power point, the voltage at maximum power point, is slightly different than temperature coefficient at open circuit voltage. I think I just explained that where I told you that this voltage will always be less than this. Slightly, it will always be less than this. So this means that every degree centigrade temperature drop below 25 degrees centigrade, the module voltage will rise by this. Take note, it's talking about drop. So if you go below 25, you're going to have a rise in voltage. But if you go above, if your temperature increases, if it goes above 25, you're going to have, instead of a rise in voltage, you're going to have a decrease in voltage. Don't get confused. You have to understand where it is moving. Is it moving towards positive, or is it moving towards below 25, or is it moving above 25? That will determine if you're getting voltage or you're losing voltage. So similarly, for every degree centigrade temperature rise above 25 degrees, the module will drop by that same amount of voltage. This is a little calculation exercise, but because of time, the solution is there, and I don't know if we have all the time for me to run through this, because there's a lot we need to cover, so that we don't spend another number of days going through this. Okay.
Chima, Chima,
hello?
I have a suggestion.
Okay.
Maybe you just explain the results based on the different scenario. Yeah, just explain the result. When the temperature is rising.
Let me just explain. Let me just explain. So now the question is asking us, what will be the maximum voltage, that is VOC, produced by the module? That's for this, sorry. That question is for these details here, the details that we have here. Now, this is the question, I mean, right? This is the details that we have. And here we are having the questions and the solution. So it's asking us to calculate the VOC. That's what it's asking us here in this question, right? So now the maximum VOC, that is open circuit voltage, will be produced at the lowest ambient temperature, okay, which is minus 10 degrees centigrade, okay? So the lowest cell temperature would be minus 10 degrees. Now, how are we going to calculate this at minus 10? Remember that the VOC will always be greater than the VMPP, like I told you before, okay? So now, for every degree reduction in the temperature from the standard test condition, we are going to check the number of degrees it's less from 25, and we multiply it by the coefficient, that voltage coefficient. So that's what we just did here. So the VOC is minus 10 degrees centigrade. That's the VOC, okay? Now the standard test condition, now the voltage at that VOC is this, 43 points. No, the voltage at standard test condition is 43.24. This is the voltage at maximum power points, okay? That is 25 degrees centigrade. I'm trying to get my cursor. So this is the voltage at 25 degrees centigrade, right? So now we have to add, because you're reducing, you're going down from 25 degrees centigrade, so meaning that your voltage will increase, right? So let us calculate the number of degree centigrade reduction from 25. So we have 25 minus 10, okay? 25 minus 10, then you times it by the coefficient. This coefficient for every degree rise or drop in temperature, you now times it. So when you do this, when you execute these calculations, you're going to have 49.14. So this becomes your open circuit voltage. Does anyone have a question at this point?
No, it's clear. This is straightforward. It's okay.
This is straightforward. Okay.
Yeah.
Okay. Thank you. So the same thing applies when you're looking for your V voltage at maximum power points and all of that. So it's
hello.
Hello. I can hear you.
The minus 10 degrees. How did we get that?
It was given
Okay, in the question.
It was given in the question, yeah.
From minus, okay, that's okay, sorry.
Yeah. So they're it's just the same thing, that we have in the other. So I just wanted to explain one. We use that concept, you understand every other one is the same thing. So now we're going to talk about orientation and tilt angle. I said we'll come to this, right? So now orientation and inclination tilt of a PV model. How do you tilt your PV model? You don't want to install trackers, but you want to make it fixed, but you still want to get the best out of your system. How do you do that? So the PV model's orientation and inclination, we'll talk about inclination. Some other people use tilt. They all mean the same thing. So they significantly affect the amount of irradiation that the surface receives, and hence the amount of energy that will be produced. Okay, so in the northern hemisphere, the PV model should be facing south. In the northern hemisphere, the PV model should be facing south. There's a diagram to explain this, but just keep this in mind that when you're in the northern hemisphere, your PV model should be facing south. So in Nigeria is in the northern hemisphere. Just take it. Nigeria is in, so even if you're in the north, or you're in the south, or you're in the east, or you're in the west, your PV model should be facing south. Just use your compass and determine where the south is. Your PV model should be facing south. It's the rule of thumb. Yes.
Okay. You have answered my question.
Okay. Yeah, I told you we'll come to that. So, yeah. So in the southern hemisphere, if you're in the southern hemisphere, I'm trying to remember countries that are in the southern hemisphere, but for Nigeria, we are in the northern hemisphere. So if you're in a country, assume you're developing for a country that is in the southern hemisphere, then your PV model should be facing north. Okay, so now this guarantees the maximum irradiation level on the PV model throughout the year. In regions close to the equator, the orientation is less important. So now you have an equator, like a center line, then if you're moving to a certain direction, you're moving to the north. If you're moving to another certain direction, you're moving to the southern hemisphere. So if you're in the southern hemisphere, your PV model should face north. If you're in the northern hemisphere, your PV model should face south. So what happens when you're in the equator at the center? So you just drop your PV to the flat, which means you're almost standing directly to the sun. That's what this is trying to tell us. Okay, so the optimal tilt angle of the PV, now, we are talking about the orientation. Where should you face your PV? Now, we've answered that. If you're in the northern hemisphere, face it to the south, which Nigeria is. Now, what angle are you going to tilt it? What angle are you going to raise it? How do you determine the angle? Now, this is how you do that. Now, the optimum tilt angle of the PV models depends strongly on the location. So you cannot be installing in Kaduna, and you're using the same tilt angle when you're installing in rivers. Okay, so how do you now determine your tilt angle? As a rule of thumb, the model should be tilted to an angle equal to the latitude of your installation site. So you need to understand some certain level of geography. You need to know what the latitude. You can go to Google and check the latitude of your installation site. Whatever latitude your installation site is, make sure your tilt angle is equal to that latitude. Okay, latitude is in degrees, like angle and all of that. So that determines the tilt angle of your PV model. Okay, so Nigeria is situated in the northern hemisphere, like I said. So the latitude for Nigeria is between 4 degrees to 14 degrees. So if you're installing a solar PV in Nigeria, I don't expect it to be more than 20 degrees. Your tilt angle in Nigeria, anywhere in Nigeria, I don't expect it to be more than 20 degrees. But there are exceptions. So if the roof where you want to install that, okay, yeah, so that's it. Let me just read from what I have here.
Hello.
So, okay, go ahead. Someone has a question?
Yes, you're talking about the tilt angle between 4 degree and 14 degree. Now, if I decide to tilt mine at 14 degree, what would be the difference between someone who tilt is at 4 degree?
So now the reason I say between latitude 4 degree and 14 degree, if you're towards the south, I think it's about 4. But if you move, now this is for entire Nigeria. This 4 to 14 is for entire Nigeria. So depending on the region where you want to do this installation. If you're in the south, I think it's less than, I think it's about 4. So I've forgotten how it moves, whether it's from the south to the north, but it's between 4 and 14. So determine the latitude of where you're installing that solar PV system, and that will become your tilt angle, right? That's where you're going to get the maximum irradiation from the sun. As long as you're facing south, then your tilt angle should be between 4 to 14. Okay. Now, there are some roof-mounted PV systems. Okay. You cannot reconfigure the roof because the roof is already there. Okay. So in such cases, if you look at the cost for you to reconfigure that roof, it does not make sense compared to the cost of additional energy you're going to get just because you want to get the right tilt angle. So in such cases, you just go ahead and install on the roof, irrespective of the tilt angle, but make sure it's not, the tilt angle is not vertical. Okay. So that's why you see some solar installations on the roof. They just go with this roof angle. They don't have to, because you cannot ask the owner to go and re-roof his house because you want to install solar panels. Okay. So that's the exception I'm talking about. So in regions close to the equator, the most solar irradiation is captured if the PV module is flat. Remember I talked about equator.
No, sorry, sir. The audio was breaking. I didn't get your last explanation about the, when you said if the roof is tilted at an angle greater than the 14 degree, what do you need to do to get good irradiance?
There is nothing you can do in that situation. Just go ahead and install your panels at the tilt angle of the roof. Because if you want to change the roof angle, it's going to cost a lot for how much energy you're going, for how much additional
Well, sometimes there is, like in my area here in Nigeria, there is one roof they call send down the rain.
Yes.
That angle sometimes is more than 60 degrees. Yes.
Yeah, no, I know,
it's not situation and far out. It will, by the time this one is, because currently I'm doing small installation. In fact, so we're having that challenge. You come there at the peak of the sun, you check your charging current is very low.
These are the problems. So
now we told the guy, we told the guy, okay, we'll bring the panels down, but he doesn't have space in his compound. The compound is tight, so that we can use this thing. What is it called?
Ground mounted.
Yes,
it's a problem. It's a problem. I must say yes, it's a problem. Yeah. So, but I mean, you cannot tell the man to go and remove his roof because he wants to install a panel. So it's a problem.
Well, you know, some of these clients, they don't want to know. After I spend by panel, you know the noise now. It's not working. It's
no. Educate them before you do the installation.
Okay. Can I chip in something in this situation?
Yeah, please go ahead.
Okay, in that situation, I think it could be best to probably install the panel towards the top, the upmost top of the roof.
Okay.
Yeah.
But it doesn't change the angle.
If you see that it's the same angle. If it's up, it's down, it's the same angle.
No, because of the way the roof is being structured already, as you said, send down the rain. So it is actually structured in a way that rain can easily fall down. So if the panel is a bit towards the tip top, I think it can increase the power generated from the panel.
Okay.
Yeah.
Okay.
Can capture more irradiance. Yeah.
Okay, so in regions close to the equator, I was trying to talk about the equator. If you're on the equator, just make it flat. However, it's not advisable that you leave it flat so that it can clean itself. So if there are some debris on it, it can fall off. Okay. So in regions close to the equator, the most solar irradiation is captured if the solar PV module is flat. However, in practice, a minimum tilt angle of 10 to 15% is recommended to allow for self-cleaning. Now, this is the diagram I was talking about. Okay, I think Nigeria, if you can see my cursor, Nigeria is somewhere here. Now, this is the northern hemisphere. This is the equator. Okay, Nigeria is somewhere here, somewhere around here. Okay, so now this is the southern hemisphere. If your solar panel is on this side, then it should be facing northern hemisphere. If it's on this northern hemisphere, it should be facing southern hemisphere. This is what I was trying to explain. Okay, so this is just the diagram to explain that. So now let us go into solar yield estimation, energy that comes out from your solar system and all of that.
Chima, sorry, before you start that, I just have one question to ask. Okay. It's regarding the temperature coefficient and its effect on voltage, voltage increase or decrease.
Yeah.
Now, I'm just looking at it. The standard test condition is, say, 25 degrees C.
Yes.
Here in Nigeria, there seems to be a lot of discussion, not only Nigeria, everywhere, I think, in the world, where you have the dry areas where the sun shines a lot. It's favored, solar installations, even looking at it for large-scale installations. Now, with that kind of condition, if you take, say, Sokoto, Katsina, Maiduguri, the temperature is very, very hot. While if you go to Europe, the temperature is in the minus degree C region. So, considering that, how would that now affect the efficiency of the modules because of the high level of temperature that is experienced in this kind of regions or areas?
Okay, good. I had, when I was talking about the different kinds of panels, I told you we have 3 different kinds of panels. We have the monocrystalline model, we have the polycrystalline, and then we have the thin film. They all have different characteristics. Now, the thin film has a higher resistance to temperature compared to monocrystalline and polycrystalline. So now look at if you're looking at this diagram, this is temperature gradient across Nigeria. So if you look at those regions that you mentioned, the northeast, this region that are red, Kano and Katsina, Sokoto, and the rest of them. We find out that they have a higher temperature. So if you're installing a solar PV model in this region, it only makes sense that you use a PV model that has a lower or a higher resistance to temperature change, which is the thin film model. So that's why it's important that you understand all of this so that you don't go and install. So if you install those polycrystalline or monocrystalline in this region and temperature rises, it's going to affect the output, the yield from the solar model. And if you had promised the client that this solar system can produce this amount of energy, it will begin to fail, and the client will come back to you and begin to complain. So that's why it's important that as engineers, we understand all of this, what affects the yield and the design of solar systems. So we can be able to do this professionally. You can advise your clients, go to the region, look at the map, and find out what the temperature is. They'll be able to suggest the right equipment or the right tool for your design. Okay? So back to the question you asked. If I find myself in such situation, I will go for a product that has higher tolerance for higher temperature, which is the thin film model. It is not very common in Nigeria, but I've seen few places where it is installed in Nigeria.
Okay.
Yeah.
Thank you.
Thank you. So in order to assess the energy yield of a PV system, one has to know about the available resources, the resource inputs to the PV system, meaning the solar irradiation. Now, color-coded solar resource map provide a first indication of available solar energy production potential in certain regions. So this is for Nigeria, actually. Now, the map you're seeing is showing us the solar irradiation in watt-hour per meter square across Nigeria. So if you look at the northern part of Nigeria, they have high sun intensity in those regions. Okay, but unfortunately, they also have increased temperature. Okay, so the solar system will do very well in the north, exceedingly well, but you need to put in the right tools, which is choosing the right equipment to be able to achieve that. Okay, so the input data are usually provided as an average annual sum. Now, when you look at the geospatial data and all of that, it's just an average. They don't tell you exact. So when you do your deployment, it might vary from your initial calculations and all of that. So just you have that in mind. So the darker the color, the better the resource potential. It's talking about the solar radiations across Nigeria. So resource assessment, the economic feasibility of a PV plant critically depend on its electricity yield. Of course, that's what clients want. They don't want to hear about your technologies and all of those jargons. What matters to them is the electricity that comes out of it. That's what they want. So which in turn depend on both the meteorological condition at the location and the performance of the plant itself. Remember, we've spoken so much about the weather where you're installing the solar PV, and of course, the performance of the plant itself. So the electricity yield is heavily dependent on solar irradiation level. It is essential that accurate and long-term climate data are available for the given location. Solar irradiation at a site is often stated in terms of the peak sun hours, PSH, over a certain period. Please note this, the emphasis is on peak sun hours. Peak sun hours. So if during the day, if the sun rises from maybe 7 o'clock or 8 o'clock in some cases, and it falls by 6 o'clock or by 5 o'clock, it does not mean that between 8 to 5 or to 6, that's your peak sun hour. It doesn't work that way. So I will explain this in the subsequent slide. So furthermore, component quality, plant design and layout, as well as the maintenance plan will affect the performance and consequently the energy yield of the plant. Ushe, can you please move everyone for me? If you're not speaking, please mute yourself. I just want to focus on this one and get through it. Okay, so performance ratio. Now, what do we mean by performance ratio? You will recall that I told you that, look, when you buy your PV system, there are oh my goodness, there's a sound that's coming from the background. Please, if you're not speaking, mute. I'll just do that. It's going to take me a few. Please just unmute yourself. Just unmute yourself. If you're not, mute yourself rather if you're not speaking, so it doesn't distract our conversation. Let's see where it's going. So now, remember when I told you that when you have your PV system, when you look at the label, you're going to see the characteristics. So for example, you're going to see the wattage, maybe for example, 300 watts, okay? It does not necessarily mean that when you put that PV system, when you install that PV system, you're going to get 300 watts. That 300 watt is at standard test condition. So if you subject your installation to standard test condition, you will definitely get 300 watts. So if you have a different climate environment, so what is the real performance of your PV system? What is the real performance? That depends on the weather condition of where you have installed it. So the real performance, the ratio of the actual performance divided by that theoretical output at standard test condition is what we know as performance ratio. So ideally, in the standard condition, this is how this PV panel should operate. But in real sense, in the actual sense, this is how it is performing. So we want to know the difference between those ratios. That's what we know as performance ratio. So the performance ratio is one of the most important parameters for assessing the performance of a PV plant. It is the ratio of actual plant output to nominal plant output at standard test condition. Okay. So it is determined by monitoring the actual plant output over a defined period, e.g. for 1 year, and then dividing this value by the nominal plant output in that same period. So the performance ratio will change from period to period, depending on the environmental and technical condition at the plant. A low performance ratio. Any question?
Hello. Yes.
Go ahead.
Yeah, when you talk about nominal output, we're talking about the output based on the rating.
Standard test condition, the rated output.
Okay.
Yes. Okay. So a low performance ratio indicates a high system loss. For example, due to high module temperature, like we discussed, reflection of solar irradiance from the module, soiling of the front glass, shading, component failure, mismatch module output, etc. There could be so many reasons that could affect the performance ratio. Therefore, higher performance ratio values are desirable. Okay? If you have a higher performance ratio, which means you're getting close to the theoretical design or the design output. So in contrast, performance ratio is also used with common reference values in the planning stage of a PV system. For example, a performance, now what this is trying to say that when you're doing your PV design, don't take your footage, the nameplate, the rated nameplate value. Don't take it and just plug it into your design. You have to assume, you have to make tolerance, you have to make room for losses, because the quoted capacity is at standard test condition. So you should know that your plant will never operate at that standard test condition. So you have to reduce that quoted capacity, maybe from 100, you have to come down to about 75 or 80, which that's what this slide is trying to talk about. That in contrast, performance ratio is used with common reference values in the planning stage of a PV system. For example, a performance ratio of 0.75 to 0.80 is used for grid connected PV plants and 0.65 for off-grid plants. This means that the expected gross energy production potential will have to be multiplied by the performance ratio value or reduced by 1 minus whatever performance ratio that you choose to reflect the expected production losses of the system, or the expected production after system losses. Okay, so this is just important just to make sure that you're on the safe side. If you're estimating the energy output for your PV system, it helps you to make sure that you don't overestimate the energy that will come out from that system. It puts you in a position to understand that some of the energy will be lost because of deviation from the standard test condition. So once the energy yield of the PV system has been estimated, the revenue from electricity sale can be calculated.
Hello, sir.
Yes, please.
Hello, sir.
Yes, please.
This assumption, what guides you? This choice of values, no? The PR to be 0.75 used for grid connected, why 0.65 for off-grid? What actually guides us to choose these values?
You can. These are just assumptions, okay, based on existing project and tests that has been done on existing projects. Mind you that to determine what your performance ratio is, your real performance ratio, you have to implement a project, monitor that project over a period of time, and then compare the performance with the theoretical capacity of that of the equipment. For you to determine the real performance ratio of your project. But now this is talking at your design stage, because the project is not already existing. For you to be on a safe side, you should consider this range in your performance ratio. Most times when I'm doing my calculation on energy yield, you want to calculate the amount of energy that could come out of a system, okay? When you're doing that calculation, in most cases, I use 0.75. So I discount 25%. From what the nameplate capacity is telling me, I will discount 25%. Okay. The same thing applies when you're doing your battery calculation. We'll get to that maybe tomorrow or next month. When you're doing your battery calculation, you also have to consider your depth of discharge. Otherwise, you messed your design up. You messed all this and so on. So we'll come to that. And this is the problem with some of these people who are going to the solar system without the full knowledge.
Sorry, can I just chip in too? I think what you're trying to say is that the fact that you should be looking at when you're designing, you should be looking at worst case scenarios. You know, you should be looking at worst case scenarios. In other words, no matter what happens, your performance will not fall below
yes.
You understand? Yes. I think that's what he's trying to say. Worst case scenario, so that you'll be on the safe side.
Yes, you'll be on the safe side, but I don't want to say a worst case scenario, because you could use 0.75, and when you do the actual measurement of your performance ratio, you could get 60, you could get 50. So I don't want to use it, but just to be on the safe side, like you said, you have to come down from the design, the nameplate capacity. You cannot just, if you're using a solar panel that is rated 300 watts, and your peak sun hour, I will come to peak sun hour, and maybe you're using a peak sun hour of 5, and then you now use that to calculate your energy yield for 1 year. That's 300 watt is assumed that your temperature is going to be 25 degrees centigrade. Your solar irradiance is going to be 1,000 watts per meter square. So how do you know that you're going to get in 1,000 watts per meter square for that peak sun hours? You're not sure. So just to be on the safe side, you come down to about 75. I don't want to go with the idea of worst case scenario because it could even be worse than that.
Let me also chip in this. I think in every engineering design, we always make use of this factor of safety. So in case of solar, they call it performance ratio. In water, we call it peak value. In storm water, we call it peak runoff. So it's always like a safety factor. To as you said, it's always tailored towards worst case scenario, but it depends on whether you don't want to see it from the cup is half full concept, but it has to be safety factor for me. Thank you.
Okay.
Thank you. Thank you.
Yeah, hello, sir. By implication of what you are saying now, it means the lower your PR that you choose, the more panels and more costlier the project is going to be.
Yes. That's implication as well. Yes. Okay, so
please, if you are.
Did you get me, sir?
Yes, I got you. I heard what you saying. You're correct.
Because like that work I told you about that we had complaint because of the T-tank. What we now do, we added 4 more panels before the system became stable.
Yes, that's what I'm saying. Yes, the lower your performance ratio, the more you have to add your panel to get a certain number of energy output that you want.
Excuse me, please. If you are not talking, please mute your distant please video, please,
Mike, yeah.
because it's interrupting us.
Thank you.
Oh, sorry.
Chima, you can go on. He just reminded us to mute ourselves.
Yeah.
It's a common rule.
I mistakenly muted him while he was speaking, so I want to apologize for that. Yeah, sorry.
Okay.
Yeah. So once the energy yield of a PV system has been estimated, the revenue is easy. You can then calculate how much you're going to, because of course you're doing this thing for in most cases for profitability and all of that. So now let's go into the just example of calculation of energy yield, okay, with peak sun hour. So the following equation provides a quick and simple way to estimate the energy yield of a PV plant over a particular period of time. So E here, just a moment, please. So E here represents the energy yield, and PSH, please, okay. PSH means peak sun hour, okay? And then P peak is your peak power production, okay? Then of course your PR means your performance ratio. So this is how you calculate energy yield from your project. If you want to calculate how much energy you're going to get from a particular project, okay, this is how you calculate it. First of all, you have to determine the peak sun hour. That is what this means, that how many hours are you going to get? How many hours is the sun going to be out? And like I said before, if the sun comes out by 8 and then dies down by 6, it does not mean that the peak sun hours is the time between 8 and 6, which is 12 hours. No, 10 hours. It does not mean 10 hours. Okay. Peak sun hours for us is the number of time the sun is at 1,000 watts per meter square. The number of, so if the sun is shining, for example, at 400 watts per meter square, for, okay, let me use 500, for example. If the sun shines for 500 watts per meter square for 8 hours, okay, for 8 hours, the peak sun hour is 4. Because if that sun was shining for 1,000 watts per meter square, it's only going to be only 4 hours. I don't know if that's clear. I'm trying to make you understand the difference between peak sun hours and the normal time that the sun is out. I don't know if that is clear. Okay, since I don't have any question, I believe it's well understood.
Not clear, sir.
Yeah, so
Yes,
that's clear. So for me, do we have data that can tell us the peak sun hour for different areas?
Yeah, you can get data, but of course, whatever data you're going to get, it's maybe assumption based, maybe close assumptions. They might not be exact. So for Nigeria, when you're designing for Nigeria, depending on the regions of the country where you're, depending on the region, if you're in the northern part of Nigeria, you have maybe you can use 5 peak sun hours. But if you're in the southern part of Nigeria, it's safe you use 4. Okay, but if you're depending on the location, so there are close assumptions that you can use. Yes.
Yeah. I think in the northern part of Nigeria is between 12 p.m. to 5 p.m. So which is equivalent to 5 hours, as you have said. That's when the sun intensity is normally at its peak in the northern part of Nigeria, because I live in Zaria. So yeah.
So it's good to just have.
Excuse sir.
Go ahead.
Excuse sir.
Go ahead.
From let's say sun sign from 8 to 18 hours. So you say 10 hours is not the push peak sun hour. What is the peak sun hour?
So
how do we arrive at it?
The peak sun hour is when you notice that the sun has more heat, when it's more hot. Yes, that period.
Excuse me, please. I think somebody's there's a noise from the background. There's a radio. I don't know. We should mute ourselves. Which I think we are mature enough.
Let the host mute everybody now.
Yeah, he has done that, but I mean,
he's been doing that. And
okay, look at Aliu. You are not muted. Charles, you are not muted.
I'm the one talking now. Charles is talking.
Okay, you are the one talking.
Yes.
Then let the Aliu mute himself now.
I am the one asking question.
Okay.
Interruption. We should be disciplined, I beg.
Okay, please let's comply so we can quickly round off this session because we are almost getting to the time and we take our time seriously. Our time commitment. So let me explain this again. What peak sun hours is. Peak sun hours is different from the time the sun comes out and the time the sun goes down. It's different. Okay. And I try to explain this with a simple analogy. So if now there's what we call the intensity of the sun, and it is measured in watts per meter square. Watts per meter square or kilowatt per meter square, whichever one that suits you better. But of course, when you're talking about kilowatt, you're divided by 1,000. So watt per meter square. So if the sun comes out and the intensity is 500 watts per meter square, and it shines for 8 hours, for example, it shines for 8 hours, and on the average, it maintains 5 watts per meter square. It does not mean that the peak sun hours is 8. That is the hour that the sun came out. The peak sun hours is when you now compress that 8 hours, instead of 500 watts per meter square, you push it up to 1,000 per meter square. How many hours will that sun stay? Can somebody speak to that? Hello?
Push up to 1,000.
If you push it up to 1,000 instead of 500.
That's 4 hours.
Exactly. So that is your peak sun hour, not 8. 8 hours is the time that the sun average was out, but your peak sun hour is 4 hours.
Okay. That is half of.
Yeah, half of the time that the sun was out. Because when the sun is coming out, it begins to increase. It can start from 200 watt hour, increase to maybe 400, 1,000. It can even come down to, I know it keeps what. When assuming that sun, assuming you kept it steady, I think I have an illustration for that. Okay, yeah, good. So this is what I was looking for. Okay. Now, this is when your sun comes out, it goes up, it gets to the peak, it comes down. Okay. Now you find out it didn't get to one. Now this is 1,000 watts per meter square. Sorry, I was saying 1,000 watt hour. Oh, sorry. 1,000 watts per meter square. So this is 1,000 watts per meter square. Now the sun came out, it didn't even get to 1,000 watts per meter square, and it died down. Now the sun was at around 7, and it went down around 5. Okay. Now, this entire area, assuming we assume that the sun was just came out and it started operating at 1,000 watts per meter square, which is what we have here. How many hours will it last? Okay, so the area of this rectangle here must be equal to the entire area of this sun part here. So we compress it and assume that it's shining at 1,000 watts per meter square. So how many hours will it stay? So this is what we refer to as peak sun hour. Okay, so the example I gave before, I was like, okay, the sun comes out at 8 o'clock or at 7, and for example, it maintains 500 watts per meter square until it's died down. Okay, what that means that if in our peak sun hour, instead of 500 watts, it's not going to be 1,000 watts. And if it's at 1,000 watts, how many hours would that be? Which is 4 hours. Is anyone still confused about this? Because it's important you know this. Okay,
it
so
is not clear. Let's use another value. Yeah. Assume it stays 8 hours at 400 watts per square meter.
Okay.
What will, yes.
So if it stays 8 hours at 400, so if you push it from 400 to 1,000, I think we're going to be dividing. Just a moment. Let me just do a little calculation here. But did you understand the process? What I'm trying to say here? Okay, so the reason I used 500 previously was just for ease of calculation. When I say that if it stays for 500 watts per meter square for 8 hours, then if you're now reducing that to 1,000 watts per meter square, it's going to be 4 hours. So if I'm trying to make 4 hours subject of the formula, say 1,000 times 8 over. Okay, so what you just said, that if you're doing 400, right, watt per meter square for 8 hours, and then you now push it to 1,000 watts per meter square, you're not asking us what will be the peak sun hour. So what you're going to do is that 1,000 times 8 divided by 400. Can you do that and tell us what the answer is? $1,000 times 8, that's 8,000 divided by 400.
That would be 20.
Sorry?
That would be 20.
That's 20.
That would be 20. No, it's not correct. Then the little calculation I'm trying to do here is not.
Hello, good evening. The calculation should actually
I think
400 times 8 hours divided by 1,000. It will give you 3.2 hours.
Okay. Yeah. That should be at yeah.
It will give us 2 hours, 30 minutes.
Exactly. So that's what it should be.
1.5 hours, yes. Okay, I've gotten it now.
So
I just want to be sure.
That's not what it will give you. That's not what it will give you. It will give you 32 over 10, 3.2 hours. That's what you will get. It's 400 times 8 divided by 1,000. 400 irradiance multiplied by 8 hours divided by 1,000 irradiance. It will give you a time of 3.2 hours.
Okay. Yeah.
Thank you.
Yeah, that's correct.
That's the correct calculation. Is everybody clear on this?
400 times 4 times 8 over what?
Over 1,000. If you cancel.
Okay. Thank you.
Yeah, it does it. Yeah, it's correct.
So we are all clear on this now, right? Thank you very much for chipping in that. Okay, so now we are still trying to calculate the energy yield. Okay, so we are trying to first of all get a very good understanding of what peak sun hour is, and now I think we are all on the same page. And then you're also going to multiply your peak sun hour by your peak power that is going to come out from the solar panel. You also have to times it by your performance ratio. which is less than 100%. So it's going to reduce your value actually. So now here your E represents your energy yield of the PV plant over a period of time that you want to calculate the energy yield, maybe 1 year, 1 month, 10 years, whatever it is that you want to do. Then you have your peak sun hour. We've already explained that. Then you have your peak nominal power of the plant. That is the nominal power of the plant. That's your peak. Then you have your performance ratio. I've explained what the performance ratio is, which could be between 0.65 to 0.85 or thereabout. So the peak sun hour is an imaginary case where the sun shines at a constant irradiance of 1000 watts per meter square for 1 hour. That is what I explained here, okay? So we can visualize the peak sun hour by looking at the area below the solar irradiance curve. This area must be similar to the area of a rectangle with a height of 1000 watts per meter square. The width of the rectangle determines the peak sun hour. I've already explained all this. So example, if irradiance is 1 kilowatts per meter square, how many sun hour is required to produce 4 kilowatt hour? Okay, so 4 kilowatt hour is our energy yield that we want to calculate. Okay, and we are given the peak. We are given the irradiance, which is 1 kilowatt per meter square. Okay, and I think we have to assume the performance ratio in this calculation because we are not given any performance ratio here. Or we just assume it to be 1. So now using our formula, that I've given earlier, we make the peak sun hour subject of the formula. Okay, so we are dividing the yield, the E, okay, by the peak sun hour. I think in this case, we just use performance ratio to be 1 because we are not told what the performance ratio is. So we are just assuming it to be 1. Okay. So when you do that division, you're going to get 4 hours. Okay. Assuming all other losses are neglected. Okay. So you're going to get 4 hours. So this is just a simple way to do your calculation. If you want to calculate your energy yield, or you want to calculate your peak sun hours or your performance ratio, depending on what you're given and then what you're supposed to calculate. This, you just plug it into the formula and then you do your calculation.
Hello.
Hello.
Okay, please. The peak sun hours.
Okay.
For an installed system, how do you determine it?
For an installed system.
Yeah. How can you determine the peak sun hour?
If you have the weather data of the location where you install this system. So, for example, if you have the weather, the sun irradiance is measured in watts per meter square of the area where this thing is installed. If you have the irradiance, then you can calculate your peak sun hour, and you determine the number of times the sun came out and the time the sun died down. At every point in time, at every hour, what is the irradiance? If you have all of that, and then you can create this curve that we have here. If you're able to create this curve, then you can easily calculate your peak sun hour.
Okay, that's okay.
Yeah. So this is just further example. I mean, you can see it's the same formula that I used in the previous example. Okay, but it's just trying to compare 2 projects, one in Europe, one in America. This is just, you can go through this example, the same formula, just you understand. So let us look at load profile. Load profile is critical when you're doing when you're designing a solar project. It's very, especially when you're doing for a large scale, maybe commercial purposes or on any other purpose. It's very, very critical. You cannot do without load profile because that will determine the size of your solar plant, or solar power plant, or whatever it is. So for a successful electrification project, it is necessary to conduct a precise analysis of expected electricity demand, as it has significant impact on the design and cost within the project. The system should neither be unnecessarily oversized nor undersized. System oversizing leads to high cost. System undersizing could lead to dissatisfaction of electricity consumers due to unreliable electricity supply. Therefore, electricity generation and electricity demand should be in balance with each other. Generation and consumption should somehow balance with each other. For this reason, demand analysis is required, leading to the creation of a load profile. A load profile is a graph showing a variation of electrical consumption over time. The time span can be a day, it can be a month, it can be a year. a forecasted load profile with a minute-by-minute resolution on time scale would be desirable, but usually it is not possible to predict demand with such accuracy. A load profile with an hourly resolution is a good estimate to start with. I'm just reading through this because you have this slide, you can read them. They're just literature that you can read and understand. So I want to focus more on the places that need technical explanations and all of that. So this is a load profile. This is just a sample of a load profile. You can see from morning time up to the evening time when you have your peak and it begins to die down again to here. So it is very, very important when you want to do a solar project to understand how this person consumes power. So that way you know how to size your system and all of that. Now this is a load profile, but this is a year load. Is it for what? I think okay, 1 month load profile. You can see it has a lot of data that is clustered together and all of that. So now I talked about peak demand. So your load profile should tell you where the peak is, and the thing about peak is that it determines the size of your plant. If, for example, you want to buy a generator, it is this peak that determines the size of the generator you're going to buy. So what about if you can reduce this peak? It means you can reduce the size of the generator you're going to buy, and it's going to save a lot of cost. So it is important that you look through the load profile when you're doing this thing, and then see what is actually causing all of those peaks. Sorry, I'm told us people are in the waiting room. Okay, so the peak is very, very important. Like I said, you have to try to find out what is actually causing. Hello, Engineer, are you there? Please check if there is anybody at the waiting room to admit. Let me just round up this trend. So look at the peak and they see what is actually causing that peak. Is this something that can be eliminated so that you can reduce the size of your power plant and all of that? And of course, you help your client also save money. You don't need to oversize the systems and all that. Now, the problem is this. If you size this kind of system with this kind of peak, okay, the problem is that at this every other time, you're going to have a redundant capacity that are lying waste that are not doing anything at every other time here. So is it possible to shift some of this consumption to this place? So for example, are they running laundry machine at this time? Are they using pressing iron at this time? So these are variable loads that they can shift to this point. Could they turn off their fridge or their freezers at this time so that they can, you find a way to spread it? This is where energy efficiency and energy management also comes in. Okay, and it's very, very critical and important whenever you're doing your solar project. That's why when I was starting, I started with telling us about energy efficiency and then renewable energy. These two are interwoven. They are husband and wife. You can't take them away. If you take them away, you kill the project. So it's important as we're educating people about renewable energy, we're also trying to let them know the role energy efficiency or energy management can play in their system design. So this load is significantly higher than the average supply level. The occurrence, these are just literature you can read. I've done some explanations on them already, so you can always read them. And then if you have any further questions when you read them and you don't understand them, feel free to reach out to Ushe or me myself. I'm sure you have our contact via the WhatsApp group. In general, Ushe, for those of them that have not been added to the WhatsApp group, if you add them to the WhatsApp group, they can always access us and ask us questions. If you have a project that you want to consult us to help you or want us, just feel free to share information and we'll help you as much as we can. So integration of solar generation profile into electricity demand profile. Okay, so this is a simplified daily generation profile of 8 kilowatt peak solar system. Normally, this will be your solar pack. It comes up in the morning, it gets to the peak, and then it dies down in the evening. Okay. So now this is a simplified daily demand profile. Now, what I'm trying to do here, I'm trying to combine this image. Now, this is your solar generation parts. I'm trying to combine it with this is your demand profile. This is a simplified demand profile. Okay, I'm trying to fit that solar generation into this demand profile so that you see how it looks like. Okay, so if I combine this, I'm seeing that 2 people are waiting in the room. So check and then admit them, please. I don't want to be distracted by those. So now this is a simplified demand profile. So if I put in that solar radiation into this, You see what I get? Now, this is why it is important that you determine your your load profile of your client before you go and design your system. So that at every point in time, the energy that is coming out from the sun is used, is maximized. You don't over-design. If you over-design, what that simply means, at some point, that your solar system can be redundant. So if you have a battery system if you have battery as part of your system, your battery will be fully charged. The electricity will be used in the house, and yet the power produced from the solar panel is not fully used. They have redundant energy that is coming out from the sun. So you need to optimize your design so you don't waste the cost. So looking at this now, this is a simplified solar radiation and a simplified load profile. If you see that this fits very well. So every energy that comes out from the sun will be used by this kind of load profile, okay? And every other one that is where the sun cannot meet the demand, it's now supplemented by the grid. All these gray areas are from the grid, as it's indicated here. You know, the percentage of energy that's coming from the sun is 26%, and then from the grid, you're collecting 74%. Now, in this case, you can now see that in this case now, the solar system exceeds the peak, not the peak actually, but it exceeds the demand during the sun hour, okay? So what do you now do with this excess capacity here? There are two things you can do. You can either install a battery so that at this time, this one can be stored in a battery system and then you discharge them at night, or you connect them to the grid. If you can connect to the grid where you do net metering, you can connect them to the grid so that this one can go to the grid and you get paid for it instead of wasting. So you can either send it to the grid or you store it in a battery. But in this case, it's a simplified daily profile with 10 kilowatt peak load and 11 kilowatt peak PV system installed. So in this case, it is assumed that this excess now is going to the grid. That's what it's written here. It's fed to the grid feeding. That's what is assumed in this case. Now, in this case, you find out you've not increased your solar installation. You have increased the capacity of your solar installation, right? So the more you increase your installation beyond your demand profile, then you cannot fit whatever excess you have into the grid. This is just, okay. Now, in this, I'm actually rounding up this training. So all these images are just to tell you what is possible in your design system, so that you don't have redundant capacities or you don't have wasted capacities that are not being used, okay? So in this case, you have a higher solar installation in your load profile. What do you do with it? Like I said before, it's either you send it to the grid or you install or you store it in a battery. So in this case, it's assumed that you're storing it in a battery so that during the evening time, when the sun is not out, you can actually discharge it and then use it to supplement your grid. Now, all of this is a hybrid system. It is assumed that it's a hybrid system where you have battery, solar system, and then you're also taking from the grid. So that's the assumption here. So now this is a worst case scenario whereby the sun did not come out. So if the sun did not come out, you're also assured that whatever generation that is going to come out from the grid, not from the grid, whatever generation is going out from the solar is being fully utilized by the load profile, okay? So how do you get rid of generator? I mean, how is it possible you can get rid of your generator? So I'll just quickly run over this. So now look at the first situation here. You have a generator of 20 kVA, you don't have a solar panel, and you don't have any storage. So all your supply is coming from the grid. So at this point, this 13th hour, which is actually 1 o'clock, the grid fails. When the grid fails, you're in darkness, you don't have any power supply. The same thing also happens at 8 p.m. Now, these are just assumptions, okay? So at this time, when the grid fails, you have generator actually, not that you don't have anything. You have generator to run. So you run your generator for 2 hours. 1 p.m. and then 8 p.m. That's when you run your generator. So how do you design your system so that you can get rid of these generators? So now you have your solar system that generates excess capacity. So when it is generating excess capacity, now this is the scenario 1 where you're connected to the grid. So you can feed to the grid and sorry. So now the yellow part is your sun. This green part is your grid. Okay, no, not your grid. You're feeding into the grid at this green part. The gray part is your grid. You're taking from the grid. Okay. So now what happened is this. You're connected to the grid, but once the grid fails, your solar system stops working. So you have a grid-tied inverter. Remember when I said that your grid-tied inverter should have the capacity to know when the grid has failed and it will knock off supply to the grid. It will not take power to the grid. That is what is happening here. So here, the grid has failed and then your inverter knocks off supply. So at this point, your generator is running. You're not, in fact, whatever the solar is producing is not being utilized. It's not going to the grid because you have a grid-tied system. Unless you kind of isolate it such that you're using it internally and it's not going to the grid-tied inverter. You're using it internally, then that's a different scenario. But in this case, it's assumed that it's a grid-tied inverter, and once the grid fails, your inverter knocks off supply to the grid, or you can use it internally.
Inachima,
yeah.
Can I suggest on the last day, because this is a very important something that some people would like to, instead of you kind of being in a hurry to round up, why not we leave it the last day? You do that as a case study when we'll be doing case studies.
Okay.
The reason is this: people are exiting, and I need to make some announcements, especially as regarding downloading the software for the solar application. So I don't know if it's already finished. So, but please, you have to come back to this.
Yeah. We'll come back to this. So
I come back to this because it's a take home.
Okay. So let's just conclude today's session, and because I see that some people are already leaving because states
6. It's important to always stick to time. Thank you so much. Thank you, Engineer Chima, for that. Go ahead. You want to ask a question?
Yes. Okay. In this grid connection, I did not see the output of inverter. Is it going to pass through transformer before going to the grid, or just from inverter to the grid?
It's from the inverter to the grid.
No transformation.
Sorry? No. Now, like I said, it depends on the voltage you're transmitting. What transformer does is to step down. So it moves from the inverter to the, if you're putting it at 415, okay, then 415 is what goes into the homes of the people. But if you're putting it at 11 kV, then it needs to go to a step down transformer to step it from 11 kV down to 415 before it goes into people's home.
Okay. So the output of the inverter and that of a transformer will be compatible to make it a step up or step down. Okay. Thank you, sir.
Yes. So, Engineer Chef, please, you can make your announcement and round up so we can continue tomorrow. Engineer Chef.
Okay, thank you, Engineer Chima. I muted myself, sorry.
Okay.
Thank you, Engineer Chima, for that wonderful session. I believe some of us here will agree with me that we still have a long way to go. There's so much to learn, there's so much to impact on, but time is a limitation. But I believe tomorrow we'll continue again. I'm going to end this class in the next 5 minutes. So I'm sorry and I apologize ahead of time that we're ending a bit behind schedule. Also remember that we started 10 minutes behind ahead of we also started 10 minutes behind schedule too. Now I just want to take a snapshot of our faces. I think it's becoming something that we do. Can we just on our camera for just 1 minute, please? Let me just take a snap. Thank you. Somebody already responded. Can I just see you on your camera for just a minute?
Yes, sir. I have one.
You can ask your question while the camera is going on. Just give me 1 minute, just 1 minute.
Okay, please. There's one link that was sent.
Okay.
I just changed my device now. I don't know if that link can be sent again.
I will send it again.
I changed my device now, so I can't access it. Okay.
I get you, sir. Now, at the beginning of this training, I say something. Me and Engineer Chima, we have the privilege of being among the first 25 certified energy engineers in Nigeria. Put me right. Now, this certification course is conducted by AEE, American Association of Energy Engineers. Now, it's like PMP, it's like CCP. It's a certification course that is booming in places like Canada and US, and then in Europe. So part of our long-term vision on this training is to bring people up to speed as regards writing this exam. So we'll have a WhatsApp group where we created so that we can be kind of interacting. A lot of people might want to write this exam, or you might need link or access or whatever you need. So you are free to join. All of us belong to a lot of WhatsApp group, but this one is that we believe by next year we'll go full blown on this training, so that let's have more of our engineers coming into energy auditing, renewable energy, and energy efficiency. We're really passionate about this, and we believe we're going to make headway. So that is for the group. For tomorrow's class, I want to introduce us to a software that you can use to size everything Chima have been saying. You know, we are in the age of software. After doing your load distribution, your load profile, you need now go to the software. So the software is called PVC. So let me share my screen. What I'm saying is that when this class closes, I would like some of us to download it. It's called PVC, like system. So if you go to PVC, you see it's online. You can enjoy this software for 1 month. Now let me give you the jig now. After 1 month, the software will expire. The software costs about 800 euros. I'm not asking you to go and buy the software.
Usha, are you still recording?
Oh, let me stop. Sorry.